Yes, I would like to welcome you to our sixth multimodal learning and applications workshop. My name is Bodo Rosenhahn. I'm from the Leibniz University of Hanover, and we are organizing this workshop together with Paulo Rota, who is here, Pedro Morero, he's just in the other room giving another talk and will come back later, Vittorio Morino, who's also over there and comes back here for the next session, and Michael Young, who's available online. And yeah, it's a pleasure to have you here. I personally really prefer to have workshops in front of the main conference and not just after the main conference, because then everyone is tired and there's this quite depressive mood about workshops. But in front of the main conference, I think is pretty nice. And I'm very sure that during the day, some more people will also show up. And yeah, at the moment, everyone is at breakfast and talking to others. Yeah, people haven't met for a long time. So thanks that at least you are here and that we can start. So, oh, your animation, Michael, very fancy. So this is the sixth version, and we are pretty happy that we managed to always host this workshop on major conferences in computer vision. So we started with ECCV in 2018, and then over the next years, mainly here at CVPR, also here for this year. So it's a very nice opportunity to yeah, also raise the focus on this aspect of multimodality and machine learning. We all know that the works on language and images are yeah, getting more and more attention for image generation or video synthesis, but multimodality are also important for other domains such as autonomous driving, multi-sensor fusion, and so on and so forth. And you can also see from this long-term series now that we are still not at the end of doing research in this field. And it's very exciting how this field developed over the last years. So we're also happy that we have 4 keynote speakers for this workshop here. We will start with Nico Sebe. Later on, Helge Rudin will join in. We have Alireza Fatih and Alexander Holinsky. And 2 of them will be before lunch, 2 of them after lunch. And yeah, it's very nice that we basically can also embed these keynote speakers into our, let's say, Hall of Fame of invited speakers of all the last years. So many very renowned researchers have participated here with keynotes. So like Daniel Kremer, Jitendra Malik, Antonio Torralba, Kristen Graumann, Andrew Fitzgibbon, Cordelia Schmidt, Andreas Geiger, and so on and so forth, which also showcases us that this is a very important topic for many of us here in computer vision. And so we have received for this workshop 16 submissions and organized at least 3 reviews for each paper. We had a meta review and a PC discussion of all the papers and decided to accept 9 of these papers of the submissions. It's not exactly 50% acceptance rate, but I think it still shows that we have a good amount of quality and a sufficient quality here for such a workshop at CVPR. The program for today. So first, we have here the small welcome session from myself. Then we'll continue with the first keynote given by Nico Sebe. Nico couldn't manage to come here to Vancouver, so he will give his talk online. Then we have a small coffee break and continue with the first oral session. Every speaker has around 10 minutes time for presentations and 5 minutes for question and answering. And it would be nice during the coffee break if the presenters come here to the front, and if we arrange this with the laptops here, maybe we can copy all the talks to one of the laptops to have it running in one big session at the end, because else it's always a little bit a hassle to switch over with these Zoom sessions, and yeah, so that we don't have too much delays with that. So if we manage, this would be perfect. Then we will have the second keynote by Helge on unpaired multimodal learning. We'll have a lunch break. And in the second part of the day, we will start with Alireza's keynote, have our second oral session, a coffee break, and the third oral session. And also for these 2 oral sessions, so it would be good during the lunch break to organize a presenter notebook, and also doing this coffee break for the last oral session to also organize a presenter notebook and to collect the presentations. In the late afternoon, we have Alexander's talk, and we will close the official part of the workshop at around 5 p.m. And then we have time for the poster session. So all the talks were invited to prepare posters, which will be, I think, presented downstairs in the poster hall. And yeah, and then we have also ongoing time for discussions in this field. So we would like to thank all the participants of the workshop. So we thank you for coming here. And we'd also like to thank the authors of the paper for their effort they spent into writing up the papers and summarizing their research and presenting their work here. We would also like to thank the reviewers and with that the program committee supporting us with all these reviews and also in the discussions about the papers. And a special thanks goes to our invited speakers, Nico, Helge, Alireza, and Alexander, and would like to thank the Computer Vision Foundation to support the workshop here. Okay, so with that, I would like to end the welcome session, and we can now hand over to the first invited talk, Nico Sewe, who is not in the Zoom. Okay, so since Nico is not here and not online, we will then continue with the first oral session. That's a good idea. And but then we can't organize to collect the slides, right? But anyway, yeah. So you have the program, right? Okay, so the first paper is called TFR GAN. Who's the presenter of this paper? Is it online? Shengqing Ji. Yeah, they expected to talk later, so it's a little bit. Luigi Riz, is Luigi here? I could give Joren's talk, so he's the third one, if you like.
We can start with that one.
Okay, Joren, we start with your talk. So, and then we see if Nico comes in. And okay, then let me switch over. Some other slides. Yeah, you can call him, and I will try to do the screen share again. Okay, this is the display setting. Okay, can you check? Okay, so it seems that online the slides look okay, and here the slides we also are on full screen. So let's continue with this talk. It's entitled SSGVS, Semantic Scene Graph to Video Synthesis. And this is a joint work between Yuren Kong, Jinghui Ji, myself, Bodo Rosen, and Michael Young. Michael is online available, and Yuren is online available. He's the main author of the paper, and yeah, also has the responsibility and deserves the honors for this work. Unfortunately, he didn't get the visa, so we decided that I will give the pitch of this talk. And if you have any more detailed questions, you can either write them in the chat or later on write him in email with that. And yeah, but we thought it would be nicer to have someone really standing here. So what is his work about? So first of all, Yuren worked during his PhD a lot on the domain of scene graph generation. And scene graph generation means you take an image as an input, and you are interested to detect objects of interest in the image in terms of bounding boxes, and these bounding boxes generates nodes in a graph, and would like to relate these nodes with edges describing the connectivity of the image content. So it's a very abstract representation of an image, and when you can see here the image in the on the right side here, you can to some extent, yeah, make it more, or you can extract the semantic information by using such a graph representation. You can use such representation to provide something like triplets, subject, predicate, objects. You can use it for image captioning or image description. And the typical challenges are that these data or for training, it's a long tail problem because you have the exponential growth of complexity with all the different options of connectivity. And there are also lots of ambiguities because there's label noise involved and so on and so forth. And so he worked a lot on the scene graph generation aspect. And in another project, we were thinking about how to use this information in a generative way. So giving a layout of an image, like you can see here in the, where I have a laser pointer here. In this part here of the image, just describing areas and the contents of these areas, our approach allows us to generate images which match such a scene graph or scene layout. So this is one of the competitors, and in this work, this was were results coming from our system. And for such settings, very often text prompts are used, and they are very intuitive, and the clip model is very famous. So this contrastive language image pair model, which can, or pre-trained model, which can be used for these tasks as well. But we are pretty interested in this abstract representation by using graphs. And in another project, he worked on so-called dynamic scene graphs, which means if you have a video sequence, you can extract the scene graphs from every image of this video sequence. But the problem is you don't capture the dynamic effects, what happens between the frames. And so if you have a static scene graph, in this case, a person is holding a bottle, and the same is true here for the other image as well. But we can see from the dynamics that the person is doing something with the bottle, which is it's drinking from the bottle. And in his ICCV paper from 21, he was able to retrieve these temporal dependencies as well in such a dynamic scene graph. So these fundamentals were basically the basis of the work he would like to have shown here at the workshop, because he's interested in using such scene graphs for video generation. And very often people think about text-to video generation, and there are also some works here at the main conference doing exactly this. But text is a little bit problematic sometimes because it's sometimes harder to capture and express the temporal dependencies in such a video sequence. And alternatively, you can also consider so-called continuous action graphs, which is a setting where the assumption is that you have for every frame a given scene graph. But this can be pretty expensive to compute beforehand. And then it's pretty hard to generalize to unseen videos. So Joren was thinking about, okay, let's make the following assumption. We have one frame given, which is the first frame. And together with the first frame, we have only at discrete time instances a visible scene graph. And this scene graph can change over time. And we would like to use this discrete information and this first image as input to generate an entire video sequence, which respects these changes here of the scene graph over time. And well, he's doing this by implementing two kinds of core modules for that. So this is the overall architecture for learning the conjoint representation between scene graphs and video contents. The lower part here is called VSG, Video Scene Graph Encoder. It has two parts. One is a spatial transformer encoding the given scene graphs of the nodes and the edges, and especially learning permutation invariance in here. Then we have a so-called temporal transformer. And here the goal is to learn the missing parts of the scene graph. So in this example, we have 8 frames. And for 3 frames, we have a scene graph given, which are here denoted as 3, 4, and 7. and the other parts here are missing. And in this temporal transformer, he is learning how could be the structure of the other missing scene graphs. And this is what he places here in a contrastive component for contrastive learning. And on the other side, we have here the images given. We place them in a frame encoder, and we want to bring the image contents and the scene graph contents together by using contrastive learning. And this is basically multimodal contrastive learning, because one modality is the scene graph and the other modality is the image structure or the image content. He implemented different loss functions. He can go over with you in the details later if you like. And but this is one of the first modules he implemented. And then he implemented a second module, which is an autoregressive transformer for the generation of the videos. So it also has two basic inputs. One is the information of the scene graph, which are given, and he's making use of the VSG encoder, which is this part here, and especially this temporal transformer, to estimate the missing scene graphs for the entire video sequence. And then we have here our input image, and we break it up in different patches. And the image information and the scene graph information is jointly or sequentially used as input for a transformer. And then we use the given information in this autoregressive framework to infer unseen information. And this is the reason why we have this kind of time delay here. So for instance, here we have the scene graph and the first component given, and we retrieve the second component. And then we have two components given, receiving the third component, and do this furthermore, till we have all the information we need to synthesize the different images. And once we have the scene graphs and the images or the image information reconstructed, we drop the scene graphs and have a decoder to reconstruct the images. And the encoder and decoder is based on a vector quantized model. And yeah, based on this autoregressive model, we then did some experiments after training. So here are some of the competitors we compared to, and as error metrics, we use it's a modification of the Fréchet inception score modified to a Fréchet video distance score, and we use the SM score, which stands for the structural similarity index known from video coding. And yeah, based on these two measures, we could show that the integration of a scene graph can really help to improve the quality of the generated short video clips with our systems. And in my opinion, the reason is because we have encapsulated global information about the structure of the image would like to see, with the more local information, the texture information, which is coming from the first input image. We also analyze different transformer layers, what is useful, but this really depends a lot on the quality of the training data. And we validated that all the different loss functions we have implemented have their impact on the overall quality. In this experiment, we analyzed where to place the information of the scene graph. And it turns out that it's useful to place it in the beginning, because then the network can see what is expected as the overall result of the image. And then we can clean it up with the texture information and make a nice image. And this is better than placing the scene graph at the end of this transformer architecture. Here are some very short video clips which are generated. So this is a person eating, someone cleaning, someone standing up, someone reading a book. And here you can see how, yeah, on these small clips, how the videos here or the input here is generated. So this is the ground truth data. These are the scene graphs which are given. And you can see here how the video is generated. Honestly, when I first saw these results, I was a little bit disappointed, because you just have the very first frame given, and then already after a few images, you have quite some drift in the quality of the texture and the appealingness of the images. But but this is, I think, just an indicator that this research is just at the start, and there are way more approaches to come in the next year. So for me, it's more like an image animation than really a video generation. But anyway, it seems to work, and here you can also see the effect of the contrastive learning. So when we place an attention on the scene graph, for instance, to the person, you can also see that in the underlying frame, there's also an attention generated to the person in the scene. And this indicates that this contrastive learning between scene graphs and images really seems to work. So to conclude this short presentation, this talk is about semantic scene graph to video synthesis. It's based on the contrastive multimodal learning framework. We have used parts of the so-called action genome data set for training and testing, and could show that we have quite some competitive performance compared to other approaches. The code and the trained models are available, so you can look up URN's homepage, write him an email, or look up his GitHub folder. You can reconstruct the results and use for your own purposes. And with that, I would like to finish my pitch. Thank you for attention. Thanks that more people joined the room, and I'm happy to take some questions. Maybe I can.
From the audience?
All right, or maybe someone from the Zoom. Joren, do you want to add something? I messed up.
No, I think it's all the things are explained very well. I really like the talk. Yeah, express all the things that I want to express. It's pretty good.
It's a pity that you couldn't make it. So yeah. Okay. Any other remarks or questions? Yeah, typical shyness in the beginning of a larger conference. That's fine. So how should we continue with the next? With Nico?
Yeah.
Okay, Nico joined. Perfect.
Yes, I'm here.
Good that you're here. So I just jumped in to give you a few minutes.
Yes, thanks.
I will just stop sharing.
Okay, I can start sharing my screen.
Yes, perfect.
Let me see. Okay, find it. Share.
Oh yes, now it is here as well. It's not in full screen mode at the moment.
It's fine now?
It is not in full screen mode. So it's now it's
I just put it in full screen.
Yeah, now it's perfect. Great. Good. So you want to introduce Paulo?
Yeah, just quickly, and so Nico Sebe, I think most of you know him. He's a full professor at University of Trento. He is a renowned scientist, so he has been general chair of many conferences, STM Multimedia and many others. He's been program chair of others like ECCV and ICCV. And so I don't know what else to say. I mean, I would just leave him the floor to his presentation.
Okay, well, thanks a lot, and well, sorry again for being late. I had some troubles first to connect, and then, well, anyway, it's now I'm here, and hopefully, well, I wish I was there, but well, like many other people, I guess, it was some conflict of a few other events that well, I had to attend last week. Okay, so what I will talk about, so this is a title is very generic, and you see, I mean, we talk about image and video generation, and my goal is to make a walkthrough so some of the recent work that will be done that were done in my group. So you see here a number of people that were contributing to this, and I will try to make a summary of what my students and the people in my group were doing. So hopefully I will be as good as Bodo was, so trying to present the work of others. Okay, so let me start with something funny. So this is some sort of animation that we did, and this is on Romanian banknotes. And so actually what we do, we are just taking these characters and they are animated. I hope also the audio would be there. Can you hear the audio?
No, from the Zoom, I cannot hear anything.
Okay, let me try to share again. Maybe I have to indicate that I have to share screen. Share sound. Okay, yes, I forgot to indicate the share sound. Okay. Now we should be okay. Anyway, I think you got the idea. So I'm not sure if you hear the audio, but it wasn't perfect. But actually, what we can do at the moment, it's very simple. And I will tell you a little bit how we did it and some of the method behind, let's say, this animation. I will start with, let's say, some kind of history. Let's say, so we started with. So I was working on this kind of generation. Well, this was in about 2008. So we talk about 15 years ago. Practically what we would do, we will have some tracking on the face. We will have a mask that you put on the face, and then you can just, take a face that you want. In this case was my former PhD advisor, Tom Huang. So you could kind of, animate your face and make the mask move around and do some, funny faces with the face. So that was a page that I took from his webpage. Of course, it's looking like a mask, so it's far from, let's say, the quality that we are able to do now. That's 10 years later, I was going to celebrate. So we had a big party when Tom would turn 80. And this is something that I did on my mobile phone. So, okay, you can put things on your face. And so, I mean, this is kind of easy. But also, I was also putting Tom's face on top of mine. And now it's much better. And this is also running on the mobile phone. It's still looking like a mask, but it's definitely much better. And well, finally, this is kind of a few years ago. This is the photo from our webpage, and my students, they just took a talking face, and they just animate me, do so take the simple the static image of myself and make me do exactly the same talking as the guy was doing. And well, the last video, so this is something that we took from the YouTube. It wasn't done by us, but so the girl in the middle, it's a driving video, and then she's kind of using our software to animate the other heads, and well, the solution is this. Okay, so you can see it's not only the facial expression, but also the eyes movement and so on. The animation here is in 2D, so there is a little bit of deformation, but for this type of videos in which you have a close-up on the face, it's looking quite reasonable, actually. Okay, so let's see how, so what we did. So we started with several things. So the first one that we started was the one in the bottom. Practically, here we had a fixed face in a neutral expression, and what we were doing, we were generating facial expressions depending on the label using a condition recurrent landmark generator. We were animating the landmarks, and then we were putting some texture mapping on top of that, and you could generate a diversity of videos. So practically, you start from a single image. You have a label of facial expression, and the goal here is to generate different sequences having the same facial expression. So practically here we had something that what we called push-pull loss. In one hand, we want to have this facial expression of the same expression of being as diverse as possible. So this will be done for data augmentation, and we show that it's really working. With also a pull loss because we want these videos, short videos, to belong to the same class. For the sake of time, I'm going to skip this part. But so that was our first attempt. Then what we started to do, we were trying to have this is in here on the left, on the top left. Practically, you have a static image, you get a target pose, and what you do, you generate the same image taken from in the target pose. And I will go a little bit in detail, so I will skip this one for now. And the last one that I will talk about is to try to do arbitrary object animation without 3D modeling. Okay, so let me start with this pose-based human image generation. Well, as you see, this is not new anymore, but practically what you have a static image. You extract a few landmarks, and you see here they are indicated as heat maps. So we have some uncertainty around the landmarks. We put it through a generation. We do some prediction, and then we compare with the ground truths. And finally, we do it in a discriminator, and we have the gun loss and indicate if it's real or fake. Okay, this works very, very fine. Of course, if you have a rigid and the points are aligned. So let's say for maps from infrared to regular map and so on. But when you don't have the task aligned, you have some problems, right? So when you have to deal with the formal object generation. And this is very simple. So if you take the situation in this example, if you would just not consider that you have the deformation model, then when you do the generation, you are going to make the correspondence between parts of the body that have nothing to do with each other, right? So we need a deformation model, and this is exactly what we do. So practically for each specific body part, right? So you can see here, so you take an image, you take the skeleton part, we just compute an affine transformation FH, which is used to move the corresponding feature map content from the source image towards the target image, And practically here, what we do, we are using this transformation, the one that we learned from the data, to move into the feature space, right? So you have a target stream. When you start with the target pose, so which is given as an input, you are computing from this pose heat map using Gaussian blurring, and then you are using this feature map, which are shuttled by skip connection from the HB stream, right? And then practically what you do, you just generate the image what you have. At the same time, you also have the source stream, in which here you are given the source image. You are computing from the source image, you are computing the skeleton part. And then, of course, the joint location in XA and AJ are spatially aligned because this is what we construct. And our goal is to generate the target image into the given pose, right? So here we are computing some deformed tensors, which are shuttled by deformable skip connections from the source stream, right? And these are some results. We started, so in this case, it's working quite well. So even if the target pose is completely different from the source image, the pose it's also oriented, so we know if it is from the front or it's from the back. So you can see in the last row that you can also generate the person, for example, so you get the source image from the front, but the target image is from the back. So what is interesting is that we are also able to, so this is something what you learn from the data set. For example, in this case, in which you have a backpack, the model is able to generate quite well the backpack on the back of the guy. Of course, this is an ill pose problem because we don't know, for example, if the backpack would have a logo or something else. Of course, we are not able to generate, or at least we can hallucinate something there. But what is interesting is that without doing anything so as you see into the target pose, there is no information about, the model also learns that if you have something, let's say, attached to your back, it must be some sort of, a backpack. I will show you some example in which this is not always working, especially when you have some kind of weird objects. This is an example in which we have a different, this is another data set, this is a diffraction data set. The main difference here is that you have a large change in scale, and it's still able to do very well. Okay, and you see the baseline, for example, is not able to reproduce a logo, while it's able to do it very well. What is interesting is that even when you are changing the pose of front to back, we are still able to recognize to reproduce quite well the texture of the t-shirt of this guy. The same with the girl. Right, you can see here there is the difference is quite substantial. You don't see the legs and so on, but we are still able to reproduce the image in the given pose. Some example for the badly generated images. Well, in some cases, especially when you have some kind of rare objects, so you can see on the top row. So I mean, we don't have so many of this kind of green backpacks, so it's not able to recognize. So you see it's kind of blended into the body part. So this is wrong, of course. Also here, when you have the purse on the last row, it's not able to recognize because we don't have a lot of images with purses. Right, so it's working when you have some errors in the pose estimation. It's having troubles when you have errors in the pose estimation, or there is some ambiguity there. You have rare object appearance and red poses. Okay. So this is working with a static image and let's say a target pose. So our goal was then now, why can't we just move towards video, right? So why don't we just do image animation? And the idea was exactly the same. So now practically you have a static image, you have a driving video from which you can extract the pose. And practically ideally would be that you can just take every frame of the driving video and reproduce and do the image animation. This is, of course, will not work, yes, because you are going to have, you need to impose some kind of temporal consistency between the frames. So this is exactly what we were looking into, right? So you have the driving video, you have a source image, and practically what you want to do, you want to have the guy in the source image reproduce the movement of the guy into the driving video. Okay. What we wanted to do here, of course, what the solution, the naive solution I was telling you, is more like doing the appearance transfer. Right, so that takes a pose in each frame of the driving video, and then you apply the pose-based image generation that I showed before with a source image and is detecting pose. Right. The problem is it will not work when the shapes of the objects are different. For example, short to tall person, and you also need to model very well the supervised motion transfer. And another thing that we wanted to achieve is to make sure that this approach is object independent. So we don't want it to work only for faces or for bodies, but you can see in the last row, and you see some example videos, we want this to work also on, let's say, object, cartoons, whatever, even if, let's say, you have to do two different objects. So you have, for example, here, I don't know what it is, it's a cat or whatever, and you have a horse, and you want the horse to do the same movement as a source animal, right? So this is, so the only constraint we have is that, of course, emotions should be compatible. Okay, of course, I cannot just put a face in here and try to animate the face like, you know, to run like a cat, because it will not make any sense. I mean, it will do something, but of course, it's going to work pretty badly. So how do we do this? So we have this in-image animation with moving key points, and I think we were one of the first to do this. And this was, as I said, it was about 4 years ago when we work on it. Practically, what we have the encoder-decoder solution as a standard approach. So we have this motion transfer. You have some key point detector, and from there, what we do the alignment of the key points so that we obtain some displacement of the key points, and these are used to generate the image into the frame into the animation, right? So you need to make sure that we have we are dealing well with alignment. And then what we have, so we were adding on top of that, we had a motion specific key point detector. So delta here. We have a motion prediction network. Okay, and then we have an image generator that reconstructs the image that you want to do from the key point position, and so the key point delta and the delta x prime of the animated video. Okay, and practically what we do, we'll go a little bit in detail in the next slide. We are computing optical flow, which is computing by this M. And then it's used by the generator to handle the misalignment between the target and the source, right? And we are using the self-supervised learning scheme. Okay, some details about motion prediction. So from the appearance of the first frame and the key points motion, we have this motion prediction network that predicts its mask for each key point and the residual motion. We call it the first order motion model because practically we are looking only at the first derivatives. Of course, if you want to do a little bit more details, you can go into more, let's say, modes of the distribution of the motion. But what we showed is that it's working fine with the first order. And then when you do at the testing time, when you do the image animation generation, the model will generate a video with the object appearance of the source image, but with a motion from the driving video. Okay, so what we do, we transfer the motion between the source image and each driving frame, and we provide a generator with a relative difference between the key points. Okay, so this is some example. You see that some of the key points that we are obtaining are not necessarily concentrating on some geometrical features, for example, on the face, but are in an unsupervised way, are one related to the motion. So, for example, learn in an unsupervised way which points are the ones that are more representative for the motion. Let me play with it. For the body, it's a little bit more clear. As you see, it's related to in a loose way to most of the joints. Okay. In the case of the robotic arm, so these are all generators. So it's not. So now you can see here. So you have the driving video. You have the first row are the static images, and practically what to do, you are just animating the robot arm to move into the new scene. And it's working quite reasonable. This is an example in which you are, moving the people according to the driving video. It's kind of easier here because we don't have background. This is a little bit more complex, in which we are using the Tai Chi data set, and you have a driving video, and we are moving the character that you see in there. So actually, the idea came from, some time ago, I was talking to one of my students. I told him, why don't you make me do the moonwalk of Michael Jackson? And this is exactly what this is about, right? So you have, this is the example with a cartoon. You have a horse and a cat, and you can just animate things. And here you can just animate faces. It's working. It's quite reasonable. In the meantime, we also managed to solve a little bit the problem of the background. In this case, it's kind of easy. For the Tai Chi, was a little bit more complex with the background. And we were comparing with the state of the art at that time, and yes, of course, ours it's better. And what was interesting was also that using let's say user study. Our methods for different data sets was preferred in an overwhelming majority to the other methods. What was interesting is that this first order motion model was very popular, and practically even the code was used by many people. So I showed you the video with the girl in the middle animating the other faces. And so this is, I'm not going to play it all, but that was, our code was tested by this guy. So what he does is a kind of technology scouter. So he's creating these 2 minutes papers. This is our paper. And practically is just taking the video.
Dear fellow scholars,
it's animating the
papers with Dr. Kara Joana
the video with his
for you to know that everybody can make videos now.
With his own resources.
Mouth movements are looking great, and eye movements are also translated into the target footage.
Yeah, so he can also play, I can play a bit around.
To make sure that they open connection here to demonstrate that it works really
But this is something done by this guy without our, I mean, we just answer some of the questions that he had about the software, but then he was using it to
help with this in the future as a service.
let's say to do his own animation.
Is that later over dinner they tend to come back to me.
Let's see.
And now please enjoy the promised footage.
Dear fellow scholars, this is 2-minute papers with Dr. Kara Zsolnai Fehér. It is important for you to know that...
Okay, so it's working quite well, even with this kind of characters. Of course, you were using it with faces. You can see that, so one thing that I didn't say is that the animation is in 2D. So when the pose is changing a lot, so you have a little bit of deformation in this particular case.
And it will be even better and cheaper than...
Okay. So one thing that we did here was then we said, now that we are able to extract the motion and do some being able to capture some the parts of the body, right? Why can't we just use also segmentation model to try to do some replacement of parts of the bodies? Okay, so here practically what we did, we leveraged the motion information to train the segmentation network without annotation. And practically what we do, we were just starting for, the source frames. We are segmenting the motion and the parts of the body, and then we can do the reconstruction. And at the testing time, we could also get the parts of the body which are well segmented. And once we have this one, we can simply replace some parts of the body with some information from the driving video. Well, so yeah, you have the segmentation module that predicts the segmentation map and the fine motion parameters, and then you have the reconstruction module, which is computing the background visibility mask and the optical flow, and reconstructs the target frame by warping the feature of the source frame and masking the occluded features. So this is some example. So here I'm showing you only the example, the part in which we are doing the part swapping. So here you can see, you can take, part of the body, like you can see in the masks that we are using. So you can take the hair of Tom Cruise and put it on top of this guy. You can also take the glasses and the nose. Like, for example, on the lower part from Michelle Obama, you can put it on the face of the other person. And it's working quite reasonable. You can take the lips. Okay, so here it's compared to the first order motion model. Practically here we have the source image, and we are using part of the source image to augment the video that it's used for as a driving video. Okay, another thing that we've been working, and this is done by a student of my colleague Aliza Ricci, but I found it quite amazing, and I'm not sure if it's Willie there in the audience. I know he's attending CVPR, and but I will try to present very quickly his work, and I believe it's very, very nice, and that's why I think it deserves really to be well presented. Okay, so actually here it's the idea of having this pliable video generation. The goal is to try to consider a set of video depicting an agent in an environment. For example, let's consider a tennis game. And different from other methods that use frame-by-frame action annotation, we assume that there is no annotation present. Okay, what we want here, we want to have the user to input the video and to allow the user to move this tennis player, this character, into the scene in a seamless way, so that it will also resemble like a real game, right? So the guy, when he moves to the right, of course, his hand will have to kind of try to be used as hitting the ball, and so on. So you can also move the guy to the net, moving around, back, and so forth. Okay. So here you produce a video where the agent acts according to the action specified by the user. Okay. So first, so the sample of the input sequence and use an encoder network to extract the frame features. These are then using the pairs of successive features to infer the action that was performed by the agent in the corresponding transition using the action network. And given the frame feature and the action, there is a recurrent model, which is used to produce the feature representing the successive states. Okay, and finally, the successive stage is analytic back to the image using the decoder net. But this is, let's say, the simple architecture, but it's produced a lot of artifacts. So then the idea was to try to kind of make some refinements. And here we provide some extra supervision. So this means that we encode back the produced frame using the encoder and the action network, right? And in this case, you can also impose different self-supervision losses on the frames, the frame features and the produced action. And you can also use some mutual information maximization loss between actions and the reconstruction action as the main driving loss for the action learning. Yeah, so then this is an unroll model over the whole sequence, right? A little bit of details. So this is for the action network. So this first encodes the frame features using a multi-layer perceptron to produce these two embeddings, which are then compared, and you take the transition between the two frames. So this will also indicate the action direction. And when you visualize in the TSNE plot, you can see that there are different types of transitions that are observed in the training videos. So practically here you are learning, let's say, from the training video that you have, what are the legitimate movements that you would have, for example, if and also the transitions. So if the tennis player is in the center of the court, you can move right, left, up, down, or in diagonal, but not many more other motions. Okay, and so you can use NLP to assign a label to each point. So here you can understand which action is done, for example, moving left, moving right, moving to the net or back, and how the action is done, right? So you are looking at the speed and the limb movement. Right, so you can specify here this variability embedding in which you specify the specific way in which an action is performed. Okay, so these are some of the actions that we learn. So learn a wide range of actions. Right, so this is the meaning of the action is consistent. It's a penalty from the starting frame of the action is applied to. Okay. This is also for it's working also for another environment. So this is for the robotic arm. You can move the arm up and down, back and forth, and so on. You can also do some interpolation. So you can also learn, for example, how a particular action is done. I don't know, if you want to, from action 3 and action 7, you can have some interpolation states in which you can do it in there. Okay, so this is just an example. Play the video. So let me tell you that this is the first variant of the method, and then we'll show you how has this been improved. So you see that from the limbs point of view, it's looking quite well, right? So when you move the person to the right, it's also taking the right pose to move the things. But for example, here the ball is missing. And also the tennis racket is missing, and this is what has been done in the next as an extension of this work. But it is already quite interesting to see that it's able to do it, to reproduce a motion quite well. And you see here which action is how you do the interpolation between different actions. Okay, the next step, and this is what Willy presented. It was last year's CVPR. Was this playable environment in which practically you don't want only to control the players, but you also want to control a few other things. You can control the style of the field, right? You can control also the camera, what you have in there, and you can also have the same possibilities as before. Right, so this is some example. You can see that you can move here. You can move the two players. Okay, you can also change a little bit the viewpoint of the camera, and it's looking quite reasonable. And you see the movement of the players is quite natural. You can also change the style of the field. Right, you can see now different court. Also, the players are dressed differently. The motions are exactly the same in these two examples. Okay, So practically what you have, it's what we had before. So you have successive images, you have this encoder part, you have the action model that is looking into the difference between different motions at this different time. And then you have a synthesis module that it's able to reconstruct the frame at the next range. Okay, so it brings you playability, right? So you can move both guys. It's multi-object. It's well, they are deformable object, of course. You can control the camera. So here it's a zoom in, for example. You can control the style, and it's quite robust actually, right? So these are some of the learned actions. You see now the clusters in which you are moving from different actions. You can move from, let's say, left to right, go towards the net, and so on for both players. Yeah. Well, there are some limitations. Some of them have been addressed in the successive work that now it's working. It has been submitted to a journal. So the environment must have a fixed geometry in this case. So we are using it, let's say, for the tennis court. But it's also working for, let's say, for some game engines. You can also do it. So the object must lie on the plane, on the zero plane, right? So, for example, in some cases in tennis, the player will also jump. So, but in this case, we don't model that, and we don't really reconstruct the complete 3D geometry of it. It's having some troubles, at least in this variant, into blurring scene and fast-moving objects, and the action capture only the movement of the player, and there is no interaction between the objects. Okay. Other than just, you could also now model the ball and you can interact with the ball. But you are, we are not, the two players are not interacting. The sense that if I move to the right or if I go to the net, the other player likely will have to come to the net as well. Okay, so what can you do beyond this? Well, this is, you can just generate large scene with manipulable object inside. We can do without object localization and camera calibration. And you can also use this environment representation to model complex games with many objects and the larger environment. The last thing that I want to tell you, it's something that, let's say, relates to the music. What you can do, you can also simply start as input with a music sequence, let's say an audio image, and you can use this one to animate a particular person to do the dancing according to the music. Right. So here, what we were doing, we have the self-frame spatial attention network, and we also have a branch in which we are modeling the temporal attention network. Right, and these are put together, and you are animating the stick models. Okay, and well, I can show you the video. So this is you are generating realistic and coherent skeleton movement. So I don't know if you can hear it, but the input, it's only the audio, and then practically you can generate different movement according to the music. So it learns, for example, for the ballet that pirouettes are important and so on. And you see it's kind of doing it quite a lot. You can also do it with some other type of music like popping. So, this is K-pop, and well, compared to different type of methods. The main difficulty here is the fact that, of course, it's very hard to have a ground truth, right? So when you have the music as input, of course, it is ambiguous. And it's kind of imagine that you go to a club and many people are dancing. They are going to dance in different ways. I think the only important aspect is here that the generated sequence is in rhythm with the music, right? So I would dance in a different way than somebody else. So there is no really ground truth. So here, what we did for the evaluation, we had a user study in order to tell that, well, a particular method is better than another method. Okay, so what we are doing at the moment, so incorporating 3D information, we try to model complex interaction between actors and between actor and the scene, right? So, for example, in the case of the tennis game, so try to have the racket and to make sure that, for example, you understand where the ball is going. And one thing that Willie did, for example, you can also put in there that a particular player cannot lose. So practically, it will go in such a way that you can drive the generation in such a way that a particular player will not lose. Another thing that we are working quite a lot on, it's a cross-modal integration between text, audio, and visual information. And then, of course, since we deal with fakes and deepfakes, we are generating scenes. We need to have more attention to privacy and the deepfake generation. So one paper that we have this year at CVPR, it's trying to generate an image which is, let's say, privacy preserving in the sense that it will keep the features of my face, but will not reveal my identity.
That's all, folks.
Okay.
Any questions?
That was all my talk. So I'm happy to answer questions.
Okay, thank you.
I see a few things.
Yeah, we have some questions. I don't know if we want to start from those from Zoom. Can you see them?
Yes.
Okay, so the first one is, dear Niku, I see that despite the motion key points given, there is still some background sticking. Do you have any idea how to suppress this issue?
So practically, we kind of solved it when we did the face swapping. So there, when you notice, we had a specific background filling module. So practically, what you can do, you need to understand which is the person mask and the background mask, and then there you would have to do some interpolation. It will never going to be perfect. So it depends a little bit on the background. So if the background is it's static, even if it's complex, then you can probably reproduce it. If the background is, let's say, moving, then it's very hard. So imagine that, I don't know, you have the person in, let's say you do re-ID into a dynamic scene in the city. So there are cars and other people moving around. That is going to be very hard to really fill in the background correctly. So it is a challenging problem, but usually what you would do, since you can apply a segmentation module, then you could try to incorporate, like we did, into the face swapping part. As I said, it's not going to be perfect, but it definitely will improve the results. And then I see that for the pliable environments, the motion of tennis players seemed quite good. Okay, he's asking about how to validate the generation results through the real tennis players. You could. This is still more like, being a game. So in the sense that, so one thing that I was talking to Willie, maybe would be interesting to put in is to not only to generate the motion of any player, but you could probably learn the style of Djokovic or whatever, Federer, and you can make your let's say generating guy to use his style. For example, I don't know, Federer on grass would go a lot to he will do serve and volley. So you could kind of impose this type of style of player to the guy, and then of course you can also validate in that way to see if it will play like Federer. But of course it's still very hard because this type of generation is not perfect. You cannot know exactly what a player or what Federer would have done in particular scene. You can always kind of, let's say, assume or hope that the motion is compatible to what the player would have done.
Okay. Any question? Yeah, please come in. I don't know if you try to speak there, and then we'll see.
Yes.
If you hear. No. So come here.
No, I cannot hear.
I'm sorry, we didn't connect the whole thing then.
Yeah. So thank you, Professor Nico. I have been using this first order motion model for a while. I think this is a really great work. One thing that I'm not really sure is I have seen a few, because I'm working on facial expression kind of animation, but it's like if I using a first order motion model, it's like transfer the motion. So there are some work they didn't use this like implicit key point detection like you use. I've also been trying to remove this thing, but I'm not really sure. Like it's like to estimate an accurate motion field. Is this key point thing really necessary or not?
Okay, so for sure there are some approaches which are dedicated to faces, and those one are working better. What you could do, and this is what we did also, so my student also was able to incorporate. So the points that we have in there are detected in an unsupervised way, but you could also impose some kind of fixed points, right? For example, the corner of the eyes or the corner of the lips and so on. That will work much better for faces. For the first order motion model, our goal was to not to make it specific for a particular object. That's why we had this kind of thing. So we wanted to have a method that will work for different type of things. So it's working for bodies, it's working for faces, and so on. But so this is what we did. If you can incorporate some geometrically, let's say, geometrical constraints, like for the face, like corner of the mouth or the eyes, and so on. So and you can just do the tracking of that particular point. It will work much better, of course. So you would have to put into so you would have to change the code that is available to be able to deal with let's say with this type of points that are going to be fixed. So you don't need in that particular case to kind of do the unsupervised points. You know, that for face, for example, these points are the ones that are going to move, and then you can do the matching between them.
Yeah. But there's some other work. They even do not use any key points. They just from the image, and they can so their input to the to auto to the encoder and decoder framework is just the source and target image, and then they can directly get the motion field from the decoder.
Well, they need to do some sort of matching anyway, so I'm not sure what they are using. Maybe some segments or some other type of thing, but for sure they have to do the matching, because otherwise it's very hard to transfer the motion.
Yeah. I believe so as well. Yeah. Thank you.
Thank you.
Any other questions? Okay, maybe just, I mean, Nico, I know we are in the same lab, right?
Sure.
It's weird to ask you a question, but maybe you can spend another few words about, what's come next, right? So what's the future of this motion transfer, especially focus on, what are the best, let's say, modalities that you can melt together in order to have this kind of work, in the future? What your take?
Well, I mean, one of the things is that, for sure that, so this is what is happening right now. People are, so for example, for the playable environment. So here, as you see, you have so what I showed is that it was a user that was kind of pressing some directions and indicating how the player will move. But will be far better, and this is what already Willy was implemented, was trying to put in some prompts, some text prompts, so you can just type in, move the player to the right, to move the player to the left, and so on. And of course, you can also do it by voice, because that will be much easier to do the real integration. So to me, the future of this is to do this, let's say, the seamless integration between different modalities, right? So you can animate the characters by using voice or text. And then what you could also do now, you can also take from the video and generate, a prompt and so on. So you can use it for, let's say, so for example, as I said, if you want to learn the style of Federer, you could also transfer that particular style into, let's say, text or so. You can also understand some of the statistics of the motion of the real player. So you can also generate, text and maybe audio and some other things. So to me, this is the thing that you can try in a seamless way to kind of move around between different modalities. What else? I think motion generation. And also generating videos. Of course, it's a complex part. So one thing that it's to be done probably, you can incorporate this one with diffusion models, because then of course the generation is going to be denser. It's going to be probably nicer. And then many people have been using control nets to try to control what's going on in there. So I think it's I think the community is going into the right direction.
Okay. Any
Hello?
last second question? Yeah.
May I?
Yeah,
Yes.
Mike.
Okay, yeah, this is Michael here, and thanks, Nisha, for
Michael.
the great talk. Well, I just have one thought after your yeah, good points. I was wondering, it would be for the motion transfer or motion generation, it would be a good idea also to extend to the multiple like humans, like interactions, for example. So there you have also have like real occlusions and all this motion dynamics. I was think that would be a way harder problem than this single human, right? That's what they've been working on many people right now.
No, absolutely. So let's say the tennis play, it's in that direction in which you have two people, but you can have four people if they play double. I mean, I think it's you need to be able to, if you are able to understand the motion laws, of your application. Let's say people walking in the street, people playing together, either it could be football or other kind of things. Then you can apply these type of constraints on the generation part. Right. So I think what is essential here is to, let's say the tennis was the first surrogate in the sense that, it's kind of, I wouldn't say simple, but it is simpler than in other cases. But indeed, if you want to make something that is realistic, you need to be able to understand what are the rules of the game or of the, let's say, the scene, the environment, and then you could start, playing into that. So one thing that we had an attempt to do it is to try to generate, let's say, people motioning into an urban environment. Okay, so for example, I mean, you generate somebody walking, but there are cars moving around. So you want this guy not to kind of, jump in front of the car. So you understand that the car is coming and then stops, for example. So if you are able to model this kind of, physical rules, then yes, indeed, you could go to something more complex.
Great, yeah, thanks.
Thank you.
Okay. So if no other, I don't see other questions from Zoom, from the room, nobody. So, well, let's thank the speaker again. And
Thank you, guys. Thanks. Sorry for not being there.
so thank you, Nico. And we can please.
Where is the speaker of the oral session? The first speaker? Yeah, but it's better to know if there is the speaker of the. Okay. Is it remotely? So we have to check. Okay, we have a coffee break now. We come back at 11 with the oral session. Thank you.
Vito, ciao. Solo per...
Ciao, com'è?
Bene, ok. Ok. Sì, ti vedo adesso così, non sapevo chi era la... Sì. Bene, ci sentiamo.
Bene, ciao.
Ciao ragazzi. Enjoy.
Grazie Nico, ciao.
It's just that I don't have to start them.
Was mine at some point failed for some reason.
Okay.
But let's see.
Yeah, what we could try. So this can be charged with USB-C. So if we take your charger, we could also maybe plug it in here. So this could be an option, then we don't need it.
Yeah, I can play with mine. Let's just. Hi.
Just for the first paper that you presented.
Yeah.
Michael is not at CVPR right now, right?
No, Michael is.
Thank you.
Sure.
No, is it? But I think.
It's okay.
We have the first.
The problem is this guy, that they have to come here to cover.
Yeah, there was some smaller Michaels.
Sì, certo. Aspetta un secondo. Non farti male. Adesso non so.
Okay, perfect. Now we see your screen. Can you put perfect? Okay, so the paper is TFR GANs, leveraging text information for blind face restoration with extreme degradation by Cheng-Xing Xi and colleagues. And the presenter is Cheng-Xing Xi. Thank you. You can start. But we are not hearing you. I suppose we...
First, can you hear me?
Try to speak.
I have
Okay.
opened. Okay.
Okay, now we are listening. Okay.
Okay.
Start again now. Perfect. Go.
First, we find it might be some problems in the face restoration because it's often challenging to restore the human face from severely degraded faces, such as the picture in the left. It's really difficult for the nowadays network or algorithm to have a better restoration results. Our motivation have tools. The first is nowadays we often use generation area and the geometric area to use to restoration human faces, and it might not be work if the human face severe is really such as has a mask decoration. So, but we can providing additional information such as text. So the text might guide the images in generation progress. So it might be have a better results. This is our motivation. And this is our network structure. And we use 2 encoders and 2 decoders. One of the encoders is the image encoders to encode the low quality images into a feature space. Another is text encoder. In this, we use a BERT encoder to Patrin BERT to use as text encoder to encode the imaging caption into a feature space into a feature space. Then we use imaging lantern encoder and text lantern encoder, sending to a text image fusion block, and finally get the final lantern code. And also, we use 2 decoders to decode the images. The first is the text guide unit decoder, which can give some more information to the style GAN decoder to lead the style GAN to generation more realistic images. And this is the agriculture of the text image fusion block. First, we concat the image embedding and the text lantern code, and then send into 6 layers of a transformer block, and finally we get the final lantern code, which combine with the text information and the imaging information. And also, we use text guide blocks in our text guide unit decoders. We use 2 mapping networks. The first mapping network is generations, 2 different features. And the first features we use to multiply with the image features. And the second feature is at the image features. Then we send these features to the style GAN decoders to guide the style GAN 2 generations more better results. And this is our result. This is our experience result. You can see at the left, we have the almost very good performance on the data set. But however, we didn't find the real world data set which has the text caption. So we can only test it on the synthetic data set. And the right is about our different blocks to the performance. And this is our video result. you can see that our methods can have a better result. And this is my different blocks which influence the network's result. You can see our final result can actually have some attributes in this text caption. Thanks for your attention. And have any questions?
Questions from the audience or online?
No.
No. So no questions. So thanks again for the presentation.
Mm.
And now we have the invited speaker, the second invited speaker today, and will be presented by Bodo.
Exactly. So maybe we first set up the hardware. Recognize that you are here. Are you on?
I think they should hear me. I'm not sure if you can. I can also just start and see. Okay, thanks. Awesome. Yeah, thanks for inviting me. This talks on multimodal learning without correspondences. And often these keynote speakers talks are about a branch of works people have done and presenting their own work. This one is more supposed to be about the open problems I see out there. And particularly in multimodal learning, where we don't actually have a good correspondence between the two modalities. Why this topic? I myself, my students, we often wonder, what are the open research problems left, right? Industry has so much money, what can we do? But actually it goes both ways. I've talked to people in industry, and they're actually encouraged by their supervisors to only work on the problems which you can solve with a lot of money, and not on the ones where you maybe need to have a clever idea to solve it. Because there's all these academics out here solving the small problems or the difficult to solve problems, which you can solve without resources. So there seems to be a bit of split, but irrespectively of where you are in academia or industry, I think in multimodal learning, there are a lot of open problems, and I want to talk about 3 main categories. So the first one is unpaired translation. You probably know it from unpaired image translation, where you start, for instance, from a photograph and you want to transfer it to a painting. You might argue it's maybe even not multimodal learning. It's somehow the same domain with 2 images, but it's actually different, right? We have painting, it's different style. So there's a small difference. And then later on, I will go towards other domains, which are very, very different. And still we have only weak correspondences. So here you have an example of a fruit fly in neuroscience experiment. So they have a special microscope on top where you can see the neural activation of the fly on the left. And what we do, we computer scientists do, is reconstructing the behavior. And so you have these 2 modalities, and it's very interesting to find correlations. For instance, predicting the motion of the animal by the neural activation, or with weather. What is the neural activation if you just have the animal motion? And yeah, you will see we have quite weak correspondences in that case, and it's really difficult to find these correspondences between the 2 modalities. And then sometimes actually there are cases where we don't have correspondences at all. This is super hard to sell to reviewers if you want to publish in this domain, but I think it's very interesting. And we human actually, we do it all the time. If you talk about some experience you had, you describe it with what? You might have a smell, but it's hard to how do you convey smell, right? You describe it with words, maybe with color. So we do this translation. If you can't see or if you can't hear, then you use sign language to convey the audio information. So we humans actually have come up with translations between domains where there's no explicit correspondence, right? The hand shapes on the right, it's just symbols, but there's no canonical correspondence to the audio we have on the left. So there are many interesting topics where you actually don't know anything about the 2 domains, but it's still important to map from one to the other, because otherwise a deaf person couldn't at all hear what I'm talking. If it's translated, they could understand it. So yeah, I'm gonna go through these 3 and tell you what I think is still big open problems, which you should be working on if you're looking for a topic. So let's go to the unpaired image translation, kind of the simplest case where the 2 domains are very similar, both images, but just coming from a different source. We've already seen in, I think, 2016 or so, this style transfer by Gattis and colleagues, and many others followed this, but they kind of solved it already at that time. Of course, we can get better and better over time, but we have seen that we can transfer from images to different styles by essentially mapping things to the features of a neural network, and then transferring some features while keeping others together. So that's kind of solved, I would say. Then afterwards, not just the overall style, cycle again came around, and now we could do a very detailed texture transfer. So map from a zebra to a horse, or horse to a zebra. I would consider that solved again. That still there's lots of things to improve on, but we get satisfactory results already. But yeah, these examples are well chosen. So a zebra and a horse have exactly the same shape. If you actually apply that on data sets where the shape differs, cycle again would fail. So what is still open is this shape transfer if you want to not just map texture to texture, but there's some different shapes in the distribution, and that shape varies a lot. And then we're going to come to other things which are still open afterwards. But let me talk a little bit about the shape transfer. So that's work we've been working in 2019. Again, that's a neuroscience example, but for now we just focus on the image domain. And yes, the neuroscience scientists wanted to have 3D motion. So they came to us, computer vision, and we said, okay, we use machine learning, that's what you use. So we need a data set, but there's no 3D data set of fruit flies available. Okay, you can annotate, that's tedious. What we have is actually, I went to a marketplace and you can get this fruit fly. I don't know why, but somebody created this fruit fly model already. You could buy it for $10. And so we can render images. It's the same type of fruit fly actually, which we had under a microscope, but there are some differences. If you look at the top row, which is the rendering, to the bottom row, The shape of the body differs. The legs are longer, thinner. There are some differences in that. And so if you just apply the style transfer from 2016, or you map features from one domain to the other, you don't get what you expect. You get the same gray style images. By the way, we have grayscale images because it's infrared. We don't want to interfere with the animal. The animal can't see infrared, so that's what we use for measuring. So it can do this color change, but it can't change the shape. And yeah, that's what we addressed. We came up with a method which transfers texture and explicitly also deforms the object. So the image on the top is now changed to have the right texture, but also the shape is transformed. And this is general, it's unsupervised. That's a nice thing. So we can also apply it to a C. elegans. That's these worms the neuroscientists like to work with, or some fish. Again, no data set available. We could do this image transfer from synthetic to real domain, and not just transfer textures, make it look nicer, but also change the shape between the two domains. So just brief overview, how does it work? Essentially, it's a two-stage process. We first deform the image with some form of a grid, and once the shape is adjusted, then we apply the cycle guide for the image transfer. So here for the C. elegans, it's a worm, but we can just start from a stick. That's our synthetic renderer. And then we learn the deformation in a cycle consistency fashion. So we have a data set of C. elegans images without any correspondence on the synthetic domain. There's no one-to-one correspondence. We render a bunch of sticks, and then we learn how to deform the sticks to look like a worm. Another nice thing is in the synthetic case, right, we know where we drew the stick. So we can also transfer the pose annotation from the source domain to the target domain. So our goal in the end might be pose estimation. So we want to know where's the head and the tail of the worm, where are the intermediate parts. And now we get this information from the synthetic domain. That's a nice thing about working with synthetic domains. You get the annotation for free. And with this explicit deformation, we can map from the synthetic domain to the real domain, even if the shape or the pose varies. Yeah, so that's what we did for neuroscientist laboratory animals, and the neuroscientists were very happy. Soon I will talk about how we can use it for neuroscience applications. I work a lot on human motion capture, so I could spend hours with that, but I want to show you one, or just highlight one case there. It's the same principle not only applies to images, but also to pose. And here we do actually have two modalities. So let me explain what's going on here. We know very well how to capture human motions indoor in a studio. That's on the left. So we can calibrate the cameras, we can triangulate, we get the 3D pose labels. But the motion is not going to be very realistic if you want to reconstruct skiing, for instance, on the right. So on the right, we have a data set with images, but we have no 3D labels. We don't know what the camera was. We only have the video. We can do 2D detection, but we never get the 3D pose by itself. And yeah, now we have the setting where we have two modalities. They are paired in the source domain, but we don't have the corresponding pair in the target domain. So now what we did is that we try to translate the motion or the poses from the source domain to the target domain so that they reproject to the 2D poses we see. And yeah, by that, again, you can train a better 3D pose estimation technique. If you're interested about pose estimation, I'm happy to talk about it, but this talk should not be so much about 3D pose estimation. All right, coming back to this image translation problem, I said texture transfer is kind of soft. Shape transfer, we did something, but it's not perfect. You need actually segmentation masks in the target domain, which may be easy to create sometimes, but it's not always easy. So there's still a lot of open room for improvement. And in particular, there's one other aspect. Let's go to the fruit fly. Right? We could get now from a synthetic domain, which looks very realistic because we did this cycle consistency domain transfer. They look very indistinguishable if you look at them from a distance. But, well, what did we start from? We had this virtual fly model. We animated the legs to kind of move randomly. But of course, that's not exactly how a fly will move. And even though we could change the shape a little, it's not, the distribution of the two is not matching. The synthetic fly is doing something very different than the real fly. So the big open problem, I think, is not just matching the texture and the shape, but also the distribution between the two. So poses which are maybe frequent in the synthetic domain, but completely unrealistic in the real domain, we should remove it if we want to use that for training. So you want to match the two distribution. And we looked into this. I had a project on it. It didn't get very far because we tried many things. We tried VAE, right? VAE is a density estimation technique. Apply a VAE on both domains and then try to see the likelihood of each of the generated image appearing. We tried something sophisticated with Monte Carlo sampling and reweighting. It somewhat worked, but the best thing actually was to apply a generative adversarial network on it and use the discriminator as a surrogate for how likely a certain image would be compared to the reference distribution. So this is a starting point for you. It's quite a mathematical domain, but I think very rich and very important next step for this image translation domain. That's for our fruit phase, but I think it's very important in general. If you look at autonomous driving, that's all about simulation, right? If you look at the big companies, they all have a simulator and they train the autonomous cars in there. Already from this image, you look at the humans, they look very unrealistic. I mean, this is Clara, so it's not supposed to be photorealistic, but we have photorealistic renderers. It's not a problem. But look at the humans; they look very realistic, just standing around, not very realistic. And so the biggest problem is actually graphics can simulate all these nice images, but the biggest problem is actually getting the parameters for our simulation. So where are the humans supposed to be? What are they doing? Are they running across the street? Or how are they interacting? That's actually the challenging problem. It's easy to create a nice looking image, but getting the image composition, the scene composition is actually the difficult thing. And that's exactly what you would have to do. If you have a simulator, you can make it look nice, but you actually need to know how to initialize your simulator. So that's a big open problem. And yeah, you can solve it maybe with this translation approach. All right. Yeah, this concludes my first part about this image translation between two kind of similar domains. I will now move on to more weaker correspondences. But I'm happy to take any question or comment if you want for the first one. Yeah. Yeah, maybe I can apply. Yeah, so. Yeah, so. Yeah, I don't want to get into all the details, but in the cycle gun, the two discriminants and so on, but you essentially you map the synthetic images to look realistic, and then the discriminator, which is applied, which is supposed to distinguish real from fake images, you apply it on both the real image and the synthetic ones, and yeah, then you can reason about depending on what the output is, if it's high or low, you can reason about how likely that image is. Yeah. 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 Yeah, that's an interesting aspect. So a big question is, should you do this in image space, or maybe use the pose estimator and then in that lower dimensional space, more meaningful space to do the discrimination? Yeah. Actually, we tried this on other data sets, street number data sets, where this is a typical benchmark for people doing the relative density estimation. Yeah, so it's unclear what we would need to do. So yeah, thanks. All right, let me move on, because I think the other two topics I want to talk about are even more interesting. So we come back to the fruit fly, but now we have a method to estimate the 3D pose. We now go over to physics and biology. They have this microscope. How it works is that they genetically modify the fruit fly, so it essentially emits light when neurons are activated, and then they have this microscope, so physics, to picture that at microscale. So yeah, that's what you see on the left. And let me play it again on the left. Okay, it's not playing. Try to play it. As you see, these are the neurons on the left. It's again an image, so it's well suited for us computer scientists to do something with this. You have to stabilize it, try to figure out where neurons are in this noisy image. And yeah, so there are big open problems. How can you relate the two domains? It's even very general. I'm not sure if we computer scientists should we do this. I mean, it's somehow images, but in the end, it's finding correspondences in two data sets. I do think we are actually quite well posed to this, because computer vision was always about finding correspondence, right? Traditional computer vision, two images, find the correspondence so you can do a 3D reconstruction. This is also correspondence finding, but there are many, many challenges. So I mentioned the noise here in the image on the left. Often there's also a temporal domain, right, a delay. So the neuron might fire, and then much later you see the reaction of the animal on the right. So, and we actually don't know what that delay is. We've been looking a bit into this. So another way of looking into the brain activation is these EEG or other methods to measure essentially the activation of individual neurons, this neurospiking signal that they can measure. Again, they have sophisticated techniques. And now the question is, can you predict that? So given just the behavior, the mouse walking, can you predict what neurons would be activated and when? When do they spike? It's super difficult because these spikes, it's a very instantaneous event. And there's this temporal delay, so you don't really know what is associated to that. So really an open problem. If you don't know what to do, this is a good way to move on. And it's very impactful. We actually run a workshop in parallel to this. So maybe in the lunch break, you can check out our posters. There's a whole workshop on CV for animals to give neuroscience better ways of estimating the motion. I'm sure they're also interested in getting better ways of getting the correspondence from left to right. So definitely check that out. And the hope would be that once we improve computer vision, once we find the correspondences, we can actually do new scientific discoveries in neuroscience. So we can enable new scientific discoveries, which I find very intriguing. So this is short because we have tried a bit. It's hard. We'll do more in the future. The last thing I want to talk about is a topic which is really to my heart. I was asking myself, what can we do with all these GANs? We can generate fake images, but what good things can we actually do with them? So we thought maybe we can go do a digital sign language, which is better than the current sign language in some way. Let's see. As said, humans do it all the time, right? Most people who can't hear or have problems hearing, they use sign language. So can we find a similar translation of audio to some visual signal, which we can then use as a sign language? And why would we need all this? So that's the first thing. We have a paper on this, but it took, I think, 2 or 3 years to publish. So the first thing people ask, or reviewers ask, is, well, why don't you just map to lip motions, right? People can lip read, and why not map audio to lip motions, and then the people trained on this, they can actually do lip reading. It's not true. You can lip read a lot of symbols, and if you roughly know the context, maybe you cannot understand all the sounds, but you can guess the words. There's a lot of guessing involved because a lot of the sounds you do have actually the same lip motion. And so at least what we should try is to disambiguate the sounds which cannot be well represented by lip motion. So it's kind of a orthogonal to that. We want to develop a sign language for whatever you cannot see in lip reading. And that's what people have done. So there's this huge speech from American Sign Language where you explicitly disambiguate the things you can't see with the sign language. But can we do better, and can we automate this? So just a warning, it's not lip synchronization. So we want to find some language that for different sounds, or for the same sounds, we want to have the same visualization. But for different sounds like ba, ba, and fa, it should be a different visualization. So maybe the color is different for ba and fa. And you might also want to encode things like the emotion while you talk. So a happy bar should maybe have the same color, but a different shape. Because that's other things in the audio signal which we would like to convey, or which you miss out if you don't translate it. And that's again something you would hardly see in the lip motion. So here's an example how this works. Of course, there's this learning phase. So let's go through that very quick learning phase for you of our digital sign language. So on the left, you see our visualization of audio. And we mapped it to the face because humans are very good at recognizing faces. So we should be able to distinguish small subtleties in there. So I will play you the video on the left. So it's different sounds, right? And every sound is visualized with a different visualization. And I will play this other reference in the end. So now that you would have to train yourself on recognizing what visual representation corresponds to what audio signal. Or in fact, if you would be deaf or hard of hearing, you wouldn't have the sound, right? You would just have someone tell you, okay, this is an alarm clock, this is a baby crying, and that's how the visualization looks like. And so on the right, I'm gonna play you now one of the sounds again, but of course without a sound, and you would have to recognize which one it was. Any guesses? Let me play the first ones again. It's tricky, right? So there would have to be some learning process. But we all learn we learn languages. Therefore, hard of hearing people, they learn sign language, so they can also learn this. And of course, you could also translate to text and so on. But when do you learn to read, right? You're 5, 6, 7 years old. So this could be applied to deaf or hard of hearing children, babies. They could already learn what a certain sound corresponds to. Any guesses now? What was the visualization on the right? Clock. I think it was the alarm sound, but it's close, right? And that's a nice observation we also made. Even though maybe single frames, you wouldn't be perfectly able to distinguish, at least not until you're well trained. It's more the rhythm. You see the rhythm of the sound, and it's actually the connection of multiple frames that you can recognize. So both the alarm clock had this regular signal, as well as the clock of the clock ticking. So yeah, you got close. But yeah, this is something which is, I think, important to understand. We are learning a mapping from audio to video, and we need to make it somehow easy to learn. But still, the human has to learn it, and we cannot do it in just a minute here in this talk. So let me give you some insights. How can we do this mapping, right? Okay, to lip motion, it's always confusing because we map to faces, but we also try digits. We're not mapping to the lip motion, let me repeat. But so if we're not mapping to lip motion, for lip motion, there would be paired data. We have a person speaking, you record a video, you have the audio, you have me speaking. But now I just want to use the face as a projection surface. How can I do this? There's no correspondence, there's no canonical mapping. So what do? We split it in two. We learn first an embedding for sound and then embedding for images on the right. And now we have to do the translation. So we have an encoder, decoder for both domains. And the idea is we use the audio encoder and map things over to the visual domain and then use the visual decoder. And so what are the constraints we can impose? Well, somehow we have to model what humans can see or perceive. So we need to find a language which we humans can perceive and easily learn. We mostly focus on the perception, but later work should focus on the learning. So the first thing is a simple smoothness constraint. If images flicker very quickly, the human visual system won't be able to perceive too. So we added the smoothness constraint to make the generated video smooth. And then the other thing is important audio features. So those which appear often should probably map to important visual features. So that's why we have this embedding, and we enforce the cycle constraints so that it can loop back, that anything you encode on the audio side, you should also be able to decode on the video side. That's a rough, and I would just say first attempt for this digital sign language. I think we can do much more, particularly on the learning. So how can we find a representation which is easy to learn for the human? And I think what we have to do is essentially have a good computational model of human perception and learning, so we can somehow backpropagate that in our embedding that we learn with machine learning. But yeah, at the end again, so what we hope to achieve is this sign language where somebody reads and in life it gets translated to a visual representation. So therefore, hard of hearing people
when
in the first case, we actually try to map the whole audio spectrum, because separating what you can see in the lip motion and what not is quite difficult. But we are working on Audio Viewer 2.0, and here we want to, we want to only visualize what we can't see with the lip motion, and we also want to choose a different visualization, not faces, but we thought about landscapes panning over as a better visualization. But yeah, it's cool stuff. The technology we use is something like Infinity GAN. Now we're looking into diffusion models. So it's a way of achieving something great with the generative models, which often can be abused for fake images and so on. So if you want to do something worthwhile, I think that's a good thing to work in, a good domain to work in. All right, yeah, that brings me already to the end of my talk. I do think there are high impact problems in multimodal learning where you don't have correspondence or very weak correspondence, and your task is actually to find the correspondence. That's what interests me. There are high impact problems. You can solve neuroscience if you're good, and other domains too, like the audio view I showed to you. So of course, this is my biased view. So I'm happy to hear your opinions. Do you know what other data sets, other domains where we have this unpaired data without correspondence, which you find interesting to solve? Let me know. I would be happy to collaborate and discuss.
Right, Edgar, many thanks for this nice insight into your recent research and research ideas. Yes, we have time for some questions or remarks from the audience or from the Zoom chat. If you check. Okay, yeah. Can you go to the microphone maybe for the others? Is that fine for you? Yeah. Yeah. Oh, this is not working, right? Or is it working now?
You can take this
Yeah,
one.
take this one here. Oh, okay.
Yeah, just come here. I think it's fine. Just stay.
Come here and ask your question.
I'm Tapas Kanando from Samsung. So there are patients who are in coma, who are not completely in coma, but they have some facial activities. In order to, and they would maybe have a trach, so they cannot speak. So is there any work done where you can communicate with them just from the facial expression? So there's enough activity going on the face and from the, and they already knew the language before they got into a coma. So is there any work?
Yeah, I think that's an interesting point. So and it's also linked, I think, for instance, Neuralink, the company, but they have a similar problem, right? You can measure something, some neural activation, but you actually don't know what the signal represents. So you have to learn a correspondence between the two. Yeah, I would love to work in this domain, and we try to do it in a way with the fruit fly and so on. But yeah, I would love to see it finally, once it works, to have it applied to humans too. I think the interesting thing is this human in the loop there, because the human would have to learn to understand as well what the sign language is, right? So the human will learn. Maybe you should start with some crude language and then improve it over time. So it's some continual learning problem even. Or maybe once we have developed audio viewer 2.0, right, we ship it out to people and people learn this language. So they will be bound to it for their whole life. What if we come up with better techniques? Now diffusion models out there, we can synthesize more visuals, but now they learned already this original language. So I think there are many interesting topics to continue to improve the language subtly, to add something on top without removing what you have learned before.
In fact, it would be a personalized language, because each patient might have a different set of disabilities.
Yeah.
A different set of expressions that they can.
Yeah, I like that view. Actually, we didn't have it, but in principle, since, yeah, we could try to even have a personalized sign language here as well. That's an excellent point. Thanks.
Maybe
yeah.
All right, thanks. Yeah.
Question two, how do you align data spaces that are totally without correspondence? I think I understand that.
Yeah. So think of these two embeddings. We learned two separate embeddings, and that's both variational autoencoders. So we assume the latent space has the same distribution, just a Gaussian distribution. That's a prior we put on the latent space. So they're supposed to follow the same distribution. And then what you would hope to is that if you map an audio feature, which is important, it maps to the center of the distribution where the Gaussian has a high probability. So if you translate it just over, you move it over to the other space, it should also be at a location which has a high probability. But yeah, the two domains might have different dimensionality. So we have a translation network. Also, this is the prior distribution, so it will not be perfectly fulfilled for every input. That's why we need the cycle constraint to actually make sure that every audio, which is important, gets mapped to a space in the visual domain, which can actually be decoded. Because often you might end up in some space which ends up, yeah, not leads just to garbage images because hasn't been seen in the visual domain. That's why you have to tie it back. But yeah, it's interesting, right? We have just very high level constraints. So things which are important in audio should be important in video. It should be smooth. And if you know more about human perception, you should embed that as also in the mapping. Yeah, in a way, yeah. I think 1 or 2 layers, yes.
Is only one direction.
Yeah, we have a cycle consistency. Yeah. I'm not quite sure what we used in the end. We played with invertible neural networks there, but I think we just learned, and then we just learn forward and backward mapping. Yeah.
What do you think about the difference of resolution?
Yeah, it's a good point, and that's actually what we faced already because audio has a very high frequency sampling frequency. So what we first do is we translate the raw audio into these MEL spectrogram, so a spectrogram representation, where you kind of have frames. So a small segment of audio is mapped to the spectrogram, and then you kind of have an image. And we made it such that the sampling rate is roughly what you would have in a video, so 30 frames per second. In that case, yes. But yeah, that's things to work on, I think, to make it less manual and more learned and more flexible. Awesome.
Quick question. You said you were working with neuroscientists on this project, but what do you think each one is the detail that they would like? What is the common ground that eventually?
So for me, as a computer vision scientist, I like the new domains. It's new problems. Just tracking these animals is incredibly difficult. But then also once you succeed, you have this other layer that they can do something with that, and they can discover new things in that domain. That really intrigues me. And for them, they can really scale up. They don't mind a lot of manual labor. So traditionally, they would annotate hundreds, thousands of frames to get the motion model. But hundreds or thousands of frames might still not be enough. If you can scale to millions of thousands, you might see very different things than just annotating very few. So I think we can discover new things you couldn't see because of the scale we can achieve with automation. So, yeah. I think we tried a different embedding, but we haven't tried really in detail. There was this difficulty in the frequency, so we needed a one-to-one mapping for this approach to work. And the easiest we saw is the MEL spectrograms. Also, that's used in there are existing visualization techniques for hard of hearing people, and they often use spectrograms. So it was natural to start from a spectrogram and see what we can do in addition. But yeah, it's an open problem. If you have any ideas, I'm happy to hear. Yeah. Yeah. No, the sampling frequency on the audio, it's literally thousands of frames per second of instances. It's an order of magnitude more, or 2 orders of magnitude more. And I think that's the best way to map currently. But I've talked to a few people, and they say if you want to work on the raw audio, you need very long convolutional kernels to work on it, and then it could work too. Yeah. Yeah, exactly. So this MEL spectrogram, it's meant to represent also the human perception. So you probably filter already stuff out, which we anyways couldn't perceive.
So now we're mostly talking about 2 modalities.
Yeah.
You think generalized evidence to modalities?
In principle, it should be getting easier if you somehow have multiple queues, but it's tricky to bring them together, particularly if they live in different spaces, different sample domains. Yeah. So I think there are huge opportunities. What I've seen in practice is the more things you combine, the easier it is to somehow converge to the mean and get just a blurry result, talking in simple terms. So yeah, definitely interesting. I haven't looked into it, so I can't comment much on it.
Maybe a short question from my side. Why did you focus on faces? Because many of these noises came from animals or other objects. So would there be a good argument to also include, for instance, other objects in there, or was it just a matter of the databases, or are we so good with interpreting faces?
Yeah, that's one of the reasons. So we humans are good at interpreting faces. And the second is that these GANs and so on, they work very well on faces. So we had we had the techniques to generate data in that domain. I guess that's a practical argument. But yeah, in the second version I just sketched is, we imagine that I'm speaking and you're deaf or hard of hearing. So you can still lip read and get a lot from it, but we just want to add this additional information. But then you probably don't want to add it on a face because you want to actually focus on my lip. So we want to have something which goes in the background and augmented reality or on the screen, whatever. More like a background image, like landscapes panning by, which gives you this auxiliary information to disambiguate the sounds you can't tell from my lip motion. So yeah, that was just a test because we had the faces working, and there had been prior work to map high-dimensional spaces onto faces. So we followed that initially because we had to start with something. But I think it's in the long run, it would be better to map to other domains. Awesome. Yeah, thanks for the rich discussion.
Yes, great. So many thanks for the talk again. How do we continue with the program? We now.
Yeah, I think we are.
The morning section is over. We start again at 1:15 with the third invited speaker.
Yeah, it was great. Thanks. Yeah.
1:15.
Simply, I'm from the neuroscience department, and so I'm pulling a lot of topics that might be interested by. And for them, for us, it's really hard. Sometimes they really work with very basic stuff, and you can. And when you tell them, okay, think about self-supervision, right? What is that? Tell them, they are like, what? We were labeling like thousands of.
Exactly.
Nice stuff.
Yeah, thanks for your insight. Do you want to chat a little more?
Yeah. So.
When visiting every weekend with his wife and kids. So we know that he gets it.
Michael?
Facial expression.
So
wait.
Hey, Paulo, you are still recording.
I'm turning it off right now because I have to charge it a bit. So
okay, but
be back in an hour.
So maybe you can.
Can you hear me? Can you hear me?
Yeah, I can. Can you hear me?
Yes.
I was telling you that you are still recording on your account.
Sorry again?
You are still recording on your account.
Yes, I'm recording. Yes, I can stop.
Okay. Is it good now? Okay, cool. Okay, great. Thank you very much. I'm very excited to be here. What I'm going to talk about today is retrieval and tool-augmented visual language models. And this is the work that we have been doing at Google Research for the last 1-2 years. So there is contribution from a lot of external and internal people at Google. So today, we are using LLMs. This is the multimodal workshop, so everybody's familiar with all of this. And there has been a lot of emergent capabilities from LLMs, such as now we are using them for translation, correct grammar, write code, create presentation, a lot of different things. And what we are going to focus mostly in this talk is adding vision to LLMs. So that would be like somebody uploads an image and do I need to be louder?
Yeah. Can you hear the speaker? No.
Okay, maybe I should use the microphone.
Just also open your webcam.
Okay, cool. So what is it better? Yeah. So what we are going to focus in this talk is adding vision to LLMs. Somebody can upload an image like this and, for example, ask the model to write a background story for this character. The model, to be able to do that, needs to fully understand the image and be able to solve that task, right? So another example is when you want the model to be able to do reasoning, fully understand the image again, understand why, for example, this image is unusual, be able to answer the question. And also there are cases where somebody is seeking for information, right? So you have an image of your plant and you're like, why this is happening to my plant and how can I fix it? And especially in the last one, in order for the model to be able to solve this, it needs to both understand fully what the image is about, understand the very fine-grained species of plant, and also be able to go bring some external information to be able to answer that, right? Now, we have made a lot of progress. Now there are multimodal models that can take both input, image and text as input and try to answer questions or caption images and so on. So one example is the Poly work, which is also from Google. Poly is a 22 billion parameter vision model and a 32 billion parameter language model. So total more than 50 billion parameters, and gets state-of-the-art results on vision language tasks. It's trained on billions of examples from Webby dataset, which has multiple different languages. And it does great on some of these examples when it's instruction tuned. For example, the first one, why is this unusual? It does a very good job fully describing what is happening in the image, why it thinks it's unusual, right? Now the question is, now are these models with tens of billions of parameters good enough to solve these tasks? And it seems not. So these are some failure examples from Poly. So for example, the image, let's say in the middle, when was it built? It needs to understand that not only this is a church image, it seems it understands that it's a church, but it doesn't know exactly which church this is, right? And also it needs to go bring additional information of when this church was built. So are there data sets? So I'm going to talk about some data sets that try to capture these cases where it's hard for the large visual language models to answer questions. And we are going to focus on those data sets, and throughout the talk, I will show you some results on them, right? So one data set that has been around for maybe a couple of years is the OKVQA. It's a data set that is focused on answering visual questions that require external knowledge. The data set maybe is, it has played an important role bringing people thinking about these cases, but it has a lot of room for improvement. Also, like there are a lot of cases in this data set that it's like when as a human you look at it, the answer is obvious. At least for humans, it's very easy to answer the questions. Now, more recently, some of our colleagues at Google Research also created some data sets which are more focused on entity recognition. So this is a data set called Oven. And for an image, you need to predict what the exact entity, let's say from a Wikipedia knowledge page, Wikipedia page this belongs to. So you need to get fine-grained recognition. And they have a lot of entities, like more than 6 million entities from Wikipedia. It's a great data set for this purpose. Another one, so these are some examples from Oven. And then the same team, they extended Oven to also require seeking external information in addition to just fine-grained recognition. So the InfoSeek data set, now, for example, it has questions like who designed this building? Now, not only you need to exactly understand which building this is, but also you need to go bring additional information to be able to answer the question. And these are some examples also from the InfoSeek dataset. And now the current state of the art models like Poly with 17 billion parameters don't do well on the InfoSeek dataset, even when it's fine-tuned on their training set. So they get up to like, let's say 20% in the best cases. Now, when you take Poly and look at their performance on previous VQA datasets like OKVQA or VQA-V2, those are much higher numbers. Now, there's another also recent paper from Google. This one is called Encyclopedic VQA. This is also similar to InfoSeek dataset. Also, Poly doesn't get very good results on this one. So what I'm going to talk about in today is how we can bridge this gap that like in this data set which require external information to answer, the current so-called foundation models are not doing very well, and how can we improve the results. So the current models look like something like this. They take multimodal input. They tokenize, let's say, the image, the text part. Then there are many layers of transformers, and at the end, they output one or multiple modalities. What we are going to do is have this middle layer where the model will go and retrieve external knowledge or external tools to help it with the reasoning. Why do we want to do this? I think there are multiple benefits of doing something like that. One is that by going and retrieving external knowledge, you can disentangle knowledge from reasoning. You can now focus the model parameters on the reasoning part and let the knowledge be retrieved externally. This is also useful when the knowledge or the facts in the world change. So let's say the name of the current president of US changes. Now you just go update your knowledge. You don't need to update the parameters of your model. If you are using tools like Google search or so on, you don't need to have their data or sensitive information. You can call them and just get benefit from them in your model. Also, in general, models become more accurate. Maybe it's possible to reduce their parameters this way. And also, when they give an answer, it's easier now to interpret why they give that answer instead of when you have just a fully black box approach. Okay, so today I'm going to talk about 3 recent works from our team, which are all in this space. The first one is Reveal. It's extending a generative model. The model takes in as input image and text and generates output text. We show how we can improve that by accessing external knowledge. Another work is RICO, which is now under review. It's very recent work. And we show that how we can have contrastive models, like, for example, CLIP, how we can improve their performance by using external knowledge. And also, last one, which is also a new work and under submission, I will talk about augmenting the models with tools. So tools could be things like Google search, image search, object detection, etc., etc. And how can you just call all these tools in a system to get very good performance? Okay, so I will start with Reveal. So in Reveal, we pre-trained our model on a large corpus of image text data. So this is more than 1 billion image text examples. These examples, for example, look like this. You have an image, and then there's a text associated with the image. What we feed to the model for pre-training is a prefix. Like, we take the first few tokens of the text, we feed it to model plus the image, and the task of the model during pre-training is to predict the rest of the tokens, rest of the text. And in order to do this, we are gonna use also somewhere in the middle of, we are gonna retrieve information from a set of external sources of knowledge. And we are gonna use this to help us with our task. The whole thing is gonna happen, like we pre-train the whole thing end to end. So the memory, how we retrieve, how we use the retrieve information in the model, the encoders, decoders, everything is trained all end to end. So I wanted to also mention that in this work, we use 4 external sources of knowledge as memory. One was WIT dataset, which is basically Wikipedia passages. It's more than 5 million image text passages from Wikipedia. There is the CC12 million dataset, more than 10 million images with their caption. There is VQAV2, which is a visual question answering dataset, and also Wikidata, which is the knowledge graph from Wikipedia. So Wikidata is also like around 5 million triplets connecting different entities of knowledge with relationships between them. And what I'm going to talk about later is how we can learn to retrieve the related information from these sources of knowledge to help our model. So the model has 4 components. It has an encoder, a memory, retriever, and generator. Encoder basically encodes the query into an embedding vector that we are going to use to retrieve the related items from the memory. And then the generator at the end is going to fuse all this information and generate the final text. So starting with the encoder, so let's say there is an input image text. We encode the text, we encode the image, and then we are going to get a bunch of tokens. We concatenate them and then feed them to a query head, which is basically a few layers of transformer, which is going to give us a query embedding. So this will be just a vector. On the other side, we have these sources of knowledge, and these are, again, image text corpus from different sources. We are going to feed, again, both the vision and text part of each of these into separate encoders. Again, get the tokens. Now we do 2 things. One is there's a key head, which is going to give us an embedding for each of these. And then there is a value head, which its job is to take these tokens and compress them into like shorter number of tokens. And then we build them, and then we build a memory out of this. And in the memory, each row, there is a key and a value. The keys are embeddings. Values are the tokens associated with each key. Now, given a query, we want to find the closest keys, which are basically, you can do a dot product, find the closest embeddings, and take their value, which is the tokens describing those sources of knowledge, and then fuse them with the queries tokens and then do the final thing, right? So this looks something like that. We find the top K items and bring their keys and values, take the values and fuse them with the tokens of the input query, and then at the end have a decoder that generates the final text. The one thing is, how do we learn this whole thing end to end? One challenge is here, given a query, we don't know which ones are the most relevant sources of knowledge, right? So the model is training from scratch. You need to you need to learn a ranking, basically. How do you rank how do you have a higher dot product between the query embedding and the keys that belong to the most related source of knowledge? This happens kind of in a weakly supervised way. The final signal, the final loss we care about is just the language modeling, which is like generating the final output. But when we bring those tokens for the values, for each key, we had a dot product with the input query, and we use those scores to reweight the tokens. And this helps the model to learn higher weights for the dot product for the related source of knowledge. So we train multiple versions of Reveal. Reveal base is a smaller one. We use this for a lot of ablation studies. The larger one is 1.4 billion, and then Reveal, what we call a Reveal, is 2.1 billion. These numbers maybe look small now, but this work was done like maybe around a year ago. And we were able to get very good results compared to a lot of previous methods. Even they had more parameters. Reveal could get like close to 60% on the OKVQA dataset. Same thing, we tried it on a OKVQA dataset, which is a newer version of OKVQA dataset. Again, focused on external knowledge, visual question answering. Also, we applied it to image captioning. So we basically fine-tune the pre-trained model and datasets like COCO, captioning, where the goal, like, you have an image and you want to predict the caption. And we got very good results also on the captioning, both on MS COCO and NoCaps dataset. Okay, so one ablation study we did was on how useful is the knowledge memory. So let's say we tried reducing the external knowledge size, like 10%, 20%, all the way up to 90%. The bottom dotted line is the black dotted line is no retrieval. The orange dotted line at the top is using all sources. And now, first focusing on the blue one, in the blue one, we both reduce the knowledge during training and during inference. So let's say if you take, get rid of 90% of the knowledge, use only 10%, you still get a slight improvement than not using knowledge at all, but not as much. I think what is interesting is the orange curve, which is during training is same as blue. So let's say we get rid of 90% of the knowledge during training, but during inference, we go back and add all the knowledge, and we get a big boost compared to the blue curve. So even if the model wasn't trained to see all the knowledge, but during inference, you could just increase the size of your knowledge memory and get improvement. Another one is that we focus on which of these 4 knowledge sources could play a bigger role. So WIT seems to have the highest usefulness. The blue shows how, like, if we only use that knowledge source alone, what performance we get. The orange dotted line at the top shows if we use all of them. And the orange bars shows the performance we get with all the other ones without that one. Right? So if we exclude WIT, for example, that's the performance we get. So it just it shows that WIT was the most useful for us, and Wikidata was the least. Here are just a couple of I don't know how easy is to see these images, but just a couple of visual results on what the top 2 retrieved items look like when we're doing a prediction. Also, we looked at how many items we retrieve, how does that change things, and also we had a perceiver which compressed the value head, and what is how much the number of tokens in the perceiver make difference. It seems as we increase K, of course the cost goes up, but we get more benefit. But also C equal 32 seems to be a sweet spot for the perceiver compression size. And finally, this also shows that as we increase the size of the pre-training corpus, we get better and better results. Okay, so just for saving some time, I'm gonna just keep going to the next one. So this is a newer work, it's a submission. So in this work, what we are starting with is a clip dual encoder. So in clip, you have an image encoder and you have a text encoder. And during training clip, we use a contrastive loss to align these 2 spaces, right? So the embedding space of the images and the embedding space of the text. And people have trained clip on millions of examples, and it works great, etc. One thing we notice is that clip does a very good job in just generic classification. So for example, let's say if you have an image of a bird, you can use the image encoder, embed that. Now you have a bunch of classes. You can also embed those using your text encoders and do a matching. So this is just zero-shot image classification. But when you want to do the same thing for fine-grained classification, which now instead of just saying bird, you want to know what species of bird you are classifying, clip doesn't perform as well. And we are trying to figure out how we can, without changing the clip embeddings, we don't want to go and retrain the whole clip model. We just want to add a small retrieval, maybe module on top to go and improve clip to do a better fine-grained recognition, zero-shot learning. So we start with the clip. So this is like you have an image encoder on the left. It takes an image, gives you a visual encoder. We show it with a blue circle. On the right, you have the text encoder. Get the text gives you a text embedding, which we are showing with a red triangle, right? These 2 are frozen. We are not going to retrain these these encoders. What we are going to do is on the left, we take the image embedding, we go find the closest images from a big corpus of image text data. This big corpus is the Webley data set. It's like billions of image text data. We go find the closest images. We bring their text. So we use their text and we fuse the visual encoder with the text embedding. We fuse the visual embedding with the text embedding of those retrieved items. So this is happening through a transformer layer, which we call it cross-modal fusion. We need to train the weights of that. On the other side, also, we do the other way around. Basically, we take the text encoder, we find the closest text from the Webley data set, we bring their images. Now we use their image embeddings and fuse them with the text embedding on this side. So now we will have this V bar and T bar, which is the fused vision embedding and fused text embedding. During our training, we are gonna only train this on a smaller data set and have losses between V and T bar, V bar and T, and also V bar and T bar. And so V and T are gonna stay constant. These are clip embeddings. But now we are gonna have these new multimodal embeddings on both sides. And it turns out they are very useful for the zero-shot fine-grained classification at the end. So basically, it starts from CLIP, trained the cross-modal fusion on CC12 million, which is much smaller than the original dataset CLIP was trained on. Use Webley as a memory, and then we evaluate on a lot of different fine-grained classification tasks. One thing to pay attention to, when we had the image embedding, we went and found similar images, but we used their text. So we call that unimodal search. So we search in the same modality, but we take the cross-modal signal. Same thing with the text. We find the closest text and take there. And the question was, why do this? Why not just bring the image embeddings? Or why not find the closest text and then bring their image? So you had like 4 different options. And it seems this option worked the best for us. So we did some ablation study. When we do this unimodal search and then do the cross-modal fusion, we get improvements, but the other cases don't give us as much improvement. Sometimes they even hurt. Also, transformer fusion is critical because we could just bring similar embeddings and do a mean, just averaging, and that doesn't help also. So just by this simple thing, we could get much better zero-shot classification results compared to the CLIP, just vanilla CLIP. Also, some experiments on the Oven benchmark that I introduced earlier, which is an entity recognition. Again, compared to other previous zero-shot methods like poly, etc., we got much better results with CLIP plus the fusion layers on top. Here also we did some ablation study on how much the external memory size matters, and both during training and also during inference. The orange curve also reduced the memory during inference, but the purple one keeps that always full. But during training, both of them, we tried reducing the memory size to see what happens. And again, it seems like the interesting thing is purple is much better than orange, meaning that you could train on smaller data during training, but at inference, adding data more and more is always helpful. Okay, so I'm gonna go through the final work, which is very recent, again, under review. It's a new trend using external tools with LLMs, right? So you have a language model, you are gonna use that as a system kind of planner. Like you want this LLM to decide which tools to use and analyze the results and then call other tools, etc., and try to solve complex tasks. Again, just reminding what are the kind of questions we are trying to answer. So we want a model which can take in an image and then answer very hard questions about this image. Some of these questions is even very hard for humans to answer, right? So if you ask me, what is this plant? I don't know. And how should I fix this? I don't know. Even if you ask this question from a human, it's interesting to see how the human is gonna try to answer this question, right? So what we tried is like we went and took a bunch of tools. We are at Google, so a bunch of Google tools like Poly, there's a VQA version, there's a captioning version, there's Google Search, Palm, which is a language model. There's also Google Lens, which itself is a collection of tools like object detection, image matching, OCR, etc., etc. And we were curious how humans are going to use these tools to answer this kind of questions, right? So we created this UI and did a small user study. So the human sees an image and a question, and they try to answer this question by using different tools, right? So we show them also a bunch of object crops. These are from the object detection. And they are going to look at these boxes, and then they are going to get a bunch of options at what they can do, right? So they can call captioning, they can submit a query to a VQA model, they can call Google Search or language model, etc. They also can go ask questions about these boxes. For example, what are the related image captions, or what entities do you find in this box, etc. Right? And we just, like, for example, a user can click on one of these and get a result like that, and they would read this and then do something else, right? So we just observe this, collect some data, and then we are using that data, basically in this work, to guide a language model to do something similar. And this is by doing two things. One is we created a transition graph looking at what humans do, like when they call a tool, then what do they do next? And also a bunch of examples, like given the current information and the current state, what did humans do next, right? So we can create a lot of examples from those. Now, this is a new trend. A lot of work's coming out. It's very hard to keep track, but so far, it seems the recent works that I'm aware of, there is first a category of works like Viper GPT, Toolformer, etc., which they take the input and the language model just in one go creates a plan or creates a code that then is executed. We found that this might not be very good because you call a tool, you don't know what answer you're going to get from that. Is that going to be useful or not? So this whole thing we think should be dynamic. So once you get an answer, now you update your knowledge. Now you decide again what to do next, right? So if this was not useful, go do something else. There are some other methods like WebGPT, React, etc., which do things in that model, but I think that using a transition graph is very helpful to also make sure these models don't fall into an infinite loop and so on. So how does the system work? There are these tools that the model can call. There's a transition graph that helps the model make decision on what to do next. And then there's a working memory that keeps updated as the model makes progress. So let's say we start from a current state. There is a LLM-powered planner. So the job of this planner, which is basically a LLM, but it looks at the current state and also looks at some examples of what humans did at this state, is basically decide what tool to call next, right? So this decides the tool and the query it wants to send to that tool, right? So that tool is called, then it gives us an output. Then the output is fed into another module, which is an LLM-powered reasoner. This module is going to take the output and try to extract the useful information from that, and also make a decision that if this was useful or not for answering the input question, right? So if it thinks now it has all the information to give the answer, it just outputs the answer, and we are done. But if it thinks the tool response was not useful, it goes back to the original state and tries to make a different decision using the planner. And if it was useful, it just updates the working memory and now goes to a new state and again back to the planning of what to do next. This is an example of how this works just for one example image. So this is an input image. And the question is, when was the drum first used for this event? So the first thing is the system is going to break this question into two questions. The first part is a visual question. So it needs to figure out in this image, what is the drum and what is the event? And then the other question would be, once you find the answer to this, now what should we query Google search, for example, and then at the end answer the question. So once you have this visual question, the model goes and looks at the objects and tries to make a decision of which object to select. Once it selects the object, it goes and looks at the similar image captions and other information and tries to extract useful information from those. And then tries to see if this was useful information or not. And if it was useful information, it could answer this visual question. Then it moves to the next stage, which is now go get information from Google search. And then at the end, output a final answer. I think the nice thing about these combining LLMs with tools and so on is if you have strong tools, potentially this could be a very complex and strong system, which also with few shot examples could get very high performance. We got very good results on the InfoSeq dataset. If you remember, I was saying Poly, for example, was not able to get good results on the InfoSeq. Even fine-tuned, it gets up to 16–20% accuracy on different sets. Our system gets more than 50% accuracy. Also, we showed results on the OKVQA dataset. Even though our model is few shot, it gets results on par with the supervised, fully supervised methods that are fine-tuned on the Poly dataset. We also did look at which tools get called the most. I think it's interesting, a statistic. And also how often the reasoner says, oh, this was informative or not informative, or I need more information. That's it. I think as a summary, basically, I went through 3 works. The first 2, we looked at retrieval, how we can improve the visual language models using retrieval. And the last one, we looked at tools. Thank you very much. And happy to take questions if there are.
Questions from the audience?
I have a question.
Can you come to the mic?
Okay.
I can repeat. Or,
okay, just
yeah.
in reveal, you showed an interesting graph for the memory that is improved if the memory is used again during the inference and not during.
Right.
Very interesting, that one. So tell us better, how can you reinsert in the memory during the inference the knowledge? So just how can you remember this sort of?
Right. So basically, I mean, during inference, you have learned to encode your query into an embedding, right? And now you also have learned how to encode external knowledge into key and values, right? So you can use those parameters to add as much memory you want, right? So you could just, given any document, I could do the multimodal embedding, get keys and values, and just increase my memory as much as I want during inference, right? Even though the model hasn't seen those documents during training, still, if they are relevant, they are going to fall into similar embedding space as the question, so we can just bring them in. Right, so basically, the model is the same. You just can increase your memory as much as you want. At the end, you are going to do a nearest neighbor to bring the top K related information.
Other questions? Please.
Thank you for your talk. In the final talk, you said you use a lot of tools. It's very interesting. So my question is, what kind of other tools can we use? So are there any requirements?
I think the requirement was that, I mean, at the end of the day, we are using LLMs, and there's a lot of prompt engineering happening, right? So the prompt engineering is basically in context learning. So every time you're calling LLM, you need to show it few examples of some scenarios like that the model had similar information, and then it made a decision, right? So if you are calling tools for which you have few examples, then you can just add those. But I think it's critical to show similar examples to the LLM to be able to make similar decisions.
A question. So if you have many tools for each step, so how do you decide which tool to call?
Basically the planner, that's planner job, right? So just to simplify it, the planner itself is a LLM, and let's say you show it an example that, for example, I had this information and I needed to answer this question. This is the tool I called, right? And you show it like 20 examples like that, and then LLM is going to make a decision. I mean, here the assumption is that LLMs are good at reasoning, So it's not just the language model, right? So they are good at understanding the context and be able to reason and make similar decisions.
Do you have a small data set?
Yeah, so basically that comes from the data we got from humans and also some just manual cleanup, right? So the humans make similar decisions. We look at what tools they call, and then you can tell LLM that, oh, in this state, that's what the human did. So do something similar. Yeah. Yeah. Yes.
It was, yeah, maybe.
Yeah.
How does the LLM retain memory of what previous client made that may not necessarily be the right decision?
Yeah, I mean, we have a working memory. Right now, the working memory is not very complex. I think that's an interesting research problem, like what should be the memory and how do you update your memory and use that for decision making. One thing we definitely keep in memory is like, if you're in a state and you made already you called the tool, we don't want to call that tool again if that was not useful, right? So next time, if you go back, you're going to call a different tool for sure.
Who was the first guy there?
Say you would add a new tool. Is the most work in the transition data, in the human collected data that you've done because the tool doesn't exist in that data set? Or?
Yeah, I think if there is a new tool, we need to somehow get some examples for that. If it's the first time, I mean, you can try to describe the tool and maybe LLM can use that to do something, but best situation is like you have called that tools among other tools and the planner knows when to call that and so on.
But the planner itself, does it also do few shots learning using examples?
Yeah, like, so there are the two places we call LLM is the planner and the reasoner, right? So the planner does few shot basically in context learning decision making of what tool to call. The reasoner gets the answer of the tools and does an in few shot example of how to bring the useful information out of that and how to decide whether now it's ready to answer or not.
Is one here and one there? First one.
Along the lines of what she asked was, you use basically the incorrect decisions to update the planner at some point?
Incorrect decisions.
Basically, so if you say, okay, try some API calls out, but some of them were useless in this context.
Right.
Can you use that to update the planner for future steps so that to improve efficiency by basically telling it, okay, these steps were wrong, don't do this in the future?
Yeah, I think that's interesting, like how you can automatically learn from things like that. For example, it could be that also you could use reinforcement learning and things like that for that. Right now we don't, but I think it's interesting to do.
Okay, so the last. Can you shout?
Yeah. Yeah, I have a question on where did you see most of the limitation of this kind of modular approach? Would you say it's the tools are not complex enough to accommodate for the task that you want to do? Would you say that the tools make mistakes? For example, if it's an object detector tool, it doesn't detect the right object. Or would you say that the reasoner is not able to put the elements it has together in an equal manner? Where would you see the competition most in that now?
Right. I think, I mean, ideal scenario would be that you have just one multimodal model that knows how, like, just retrieve information and use this. Right now, we are using an LLM, and LLM doesn't know anything about the vision part. So the only thing it knows is like what the object detection tells it about each object, and then it decides, okay, now I should use this object because it seems to be relevant to the question, but it doesn't have all the details of that object. So at the end of the day here, the LLM is only communicating in language with these tools, right? So it doesn't have all the vision signal. Maybe that's a limitation, but I can imagine you could have also a multimodal version of LLM, right? So it's something like GPT-4, which can take both image and text and understand, but also it could get benefit of other tools like search and image search and so on.
Okay, very last questions, the guy there.
I apologize if you've already mentioned this, I might have missed it. When you're collecting the data from humans about the transition probabilities, is there any sense of correctness where the human answered correctly in the end? And did you filter for that or just include everyone?
Yeah, I think we only use the ones where human answered correctly at the end. So I mean, maybe I didn't describe that, but like in the UI, there was a button for the human where they press like here. So basically on the right side bottom, they say success, found the answer, or couldn't find the answer. And we use the ones where they can find the answer. But humans make mistakes, especially at the beginning. They start using the tools. They don't know the capacity of each tool, and they gradually learn also, which is also interesting. But it's useful to take their later tries than the beginning.
Okay. So thanks.
Thank you very much.
Now we have a session of orals.
Yeah, thank you very much.
I have a question also regarding the when you add the knowledge also in line what Rita asked before, it can be done also online. So it's a mechanism in which you can learn, increase your learning with the model online. So that's the way to do it.
Yeah, I mean, for example, you're discussing Google Lens. Google Lens does that online. Like, let's say all of a sudden there's a new famous person, you will have now new knowledge pieces for them. And
the way you do it is the same how you go back, put back knowledge.
I mean, we didn't do it in this experiment, but yeah,
it's possible.
Yeah, it's possible. Yeah,
Thank you.
Yeah, thanks.
Oral session number 2, paper number 5, multi-event localization by audio-visual fusion with omnidirectional camera and microphone array, and the presenter is Ray Kawakami, sorry, from Tokyo Institute of Technology.
Hit this one, right?
Yes.
Yes. Excellent. Sorry. All right. I think I need to just share screen. Yeah, let me try. Okay, here we are. We are good. I guess we're good.
Okay. So thanks for the introduction. So this is a joint work with Wenru Zen, Ikuro Sato, Ryota Yoshihashi, and Asako Kanezaki. And the first author, Wenru, couldn't come to this venue, so I am presenting this work on behalf of my collaborators. We are all from Tokyo Institute of Technology, though Ikuro has also a position at Denso IT Lab. Okay, so the task that we want to solve in this research is audio-visual event localization. So what is audio-visual event? Well, it has both visual and audio information, and it has to be available in a video segment. And so AV localization task find the video segments, well, basically the frames that contain an audiovisual event, and then classify it into a certain category that are predefined. So there are, of course, some related studies which focus on the temporal modeling of audiovisual events with the fusion of audio and visual features. So such as those that are listed here. And how to attend by utilizing both features is an issue. But since the data sets they're working on is based on monaural audio, so it only has single channel audio. So the spatial attention on the audio features cannot be incorporated because it only has single channel. So those methods only deal with the visual attention in their methods. So therefore, they had to ignore the internal correlation, spatial correlation between the audio and visual features. So as I said, the related studies only handle with a single event. The related studies only handle with single event segments. And I think this is again due to the nature of the data set. So no spatial attention was considered in the previous method. And therefore it was hard to distinguish multiple events if there are. So inspired by a related study that proposes an active speaker localization method, which uses 360-degree video and N-channel audio. So in this work, we pay attention to the way of extracting richer spatial information from audio input so that multiple events can be finely localized with visual cues. So our purpose is to recognize co-occurring audiovisual event with richer spatial information from the audio. So in this work, we present a multi-level, multi-channel AVE dataset where videos are captured by an omnidirectional camera and audio data recorded by a 360-degree camera and also a 8-channel microphone array. And the data sets contains frames in which multiple event labels are given. We also proposed an AV localization method that early fuses features from video and multi-channel audio so that rich spatial information from each modality can be effectively integrated. We confirm that our method consistently outperforms off-the-shelf AV localization method on this MLMC AVE dataset, our dataset, MLMC AVE dataset. So we actually created this dataset in-house. MLMC AVE tries to overcome the disadvantages of the previous datasets and methods. So it uses, as I said, omnidirectional camera and multi-channel audio. And the captured scenes include complex background, and some segments can have multiple labels. So this is an example of the data sets. So here there's a man who tries to draw the container, and there is also a woman who is cleaning. So let me show you. So the okay, so she's cleaning, and the man is dealing with the drawer. So it also has some kind of sound. Okay. So this is a comparison between other data sets, such as AVE data set, Fair Play, Rec Street, and ours. So as you can see, we have multiple audio channels, and we have 660 videos, and each clip has 15 seconds. And we have 11 categories, and the examples are mainly in the indoor scenes, and the categories are like man speaking or cleaning or writing on the board, or those events that have audio information as well. And yeah, the Fair Play data set is basically for generating binaural audio from monaural audio. So it basically includes some, people playing instruments. And there is a rec street, which has 360-degree field of view, but it is again also for generating spatial audio. And yeah, so, and the category is not available. So in that sense, our data set is probably, useful for our community to detect events in 360-degree field of view. So this is our AVE localization method. So it uses omnidirectional video and multi-channel audio. And then we basically have 8 directions, but in only on for horizontal directions. So we only have horizontal resolution, no vertical resolution. So we basically just stack those 8-channel audio, just replicate in one direction, so that we have some kind of spatial information, and we concatenate the features with the videos, those of videos, and then we input just to a CNN plus LSTM plus fully connected layers to do the classification. So we did the experiment based on our data set to verify the effectiveness. And, basically we were interested in how, the audio spatial fusion would be effective to detect the events. So here are some details for the learning. And we also, so on the leftmost side is the existing one, and on the rightmost side is ours. And in the middle, those are some ablations that we implemented. So so the B, the second from the left, uses HARC, which is software to do source separation and arrival direction estimation based on the audio information. So basically, we kind of examine whether such software for audio separation would work better or not. And on the third from the left is using the attention that is generated from the audio information and video information, like the one, like the existing ones, and then use that for detecting the multiple events. And ours is kind of the most is the simplest one, but it worked pretty well. As you can see at the bottom, our method works, well, much better than the other methods on the MLMC dataset, where although, if there is only single channel audio available, then there is not much difference between the methods. But if there is multiple audio channel, then our method can detect the events fairly well. So I think this is the interesting part. So the the rows correspond to each example, and the column corresponds to each method. And on the right is the results from ours, and the green boxes correspond to the attention that are correctly estimated, and the red ones are wrong attention. So for example, on the top, attention has to be there because there is a man who is writing something on the board, and only the hours can correctly attend to that man writing on the board. And also, what's interesting in our method is that although the audio channel has horizontal resolution, but also the attention has the resolution, vertical resolution as well, because it can fully utilize the visual information as well as the audio information. Okay. So to summarize, we proposed the purpose was to recognize a co-occurring audiovisual event. And we presented a new data set for AB localization, which contains omnidirectional video and 8-channel audio. It is available on the web. And we have also developed a new model that takes spatial correlation between audio and visual features. Okay, yeah. Thanks for listening.
Okay, is there any questions from the audience?
So you're using an 8-channel audio microphone array.
Yeah.
What is the spatial distance between the microphones? And are these 8 channels really important? Did you make ablation to just use 4 or 2 of these microphones?
Well, we only tested just one single channel audio, but the microphone array is placed at the how can I say it? I think the baseline would be probably just 1 centimeter or so. So it's not doesn't have very wide baseline. But yeah, but it is placed on the circle, so it can capture all the sound from 360 degrees. Yeah, and so it's probably sufficient, and we have tried to just use the single channel audio, and then the effectiveness compared to the previous existing one, we couldn't get better results actually. Yeah, it was a bit worse. Yeah, but if we can fully utilize all the spatial channels, then it was very effective. Yeah, thank you.
Okay, I have another question. So you mentioned you're using a software which does some kind of like I expect some informing or something.
Audio.
Sorry. Yeah, I was saying that in that there is kind of attention mechanism which provides weights, which is based on an external software, which is actually doing some audio spatialization.
Yeah.
Can you expand a little bit more on that?
Okay, so it's a open software called Hark, and you can actually use multiple things with the software. But what we used was arrival direction estimation. So if there are multiple audios, then the software can detect those audios and then also estimate the incoming direction of the sound source. So it can separate those audio and also estimate the arrival direction. So by estimating the arrival direction, we can kind of put some weight to those directions, and we use that to make some pseudo attention.
Okay.
Yeah.
Have an extra question?
Yes, yes.
I think in audio area, so we can that we get audio attacks the sound. So if they come from a vocal, Do you plan to your work with the paper differently?
Well, yeah, that's something that we wanted to do, but I think we haven't put the labels for the place. Yeah. So, but it shouldn't be that difficult. Yeah. So, if we have some time, yes, we'd love to do that. Yes.
Okay, thanks again.
Thank you.
Okay, yes, we have next speaker, Zihui Xue, correct? Yeah. She's presenting the paper, Dynamic Multimodal Fusion, paper number 8.
Directly use this.
Okay, if you have uploaded the slides, or
I can. Yeah.
you can use yours. Are you connected to the Zoom link? Okay, so yeah, the Zoom link is. Did you upload the slides in the folder we provided? Okay. Yeah, if the slides are there, we can download and use them. Which one?
88.
8.
Yeah.
Oh, yeah. Floor is yours.
Hi everyone. I'm Zihui Xue from UPLT. I'm happy to share our work, Dynamic Multimodal for Fusion today. This is joint work with Professor Radu Maculescu. So we know that humans perceive the world in a multimodal way, through vision, hearing, touch, etc. To enable machines to learn from multimodal inputs, just as human beings, many deep learning approaches have been developed. Multimodal fusion has boosted the performance of many tasks. Despite these advances, it is still a fundamental challenge in multimodal learning that how to best combine information coming from multiple modalities. In fact, there are various research works that focus on developing dedicated fusion paradigms that can effectively fuse multimodal data. However, we notice that these current fusion approaches are static. Namely, they typically process all the multimodal instances in a single fusion architecture. So once the fusion network is trained, it performs static inference on each piece of data without accounting for the inherent differences in characteristics of very different multimodal data. As a motivating example, let's look at the two instances here. So for the left instance, we can easily predict the emotion of the left instance by just looking at the text modality, because this sentence, I just got finished watching an excellent movie. This sentence itself already provides very strong cues for a positive emotion. On the other hand, it is quite unlikely for us to directly predict the emotion for the right example by just looking at the text modality. Since this sentence, I wish that it would have been a guy. It's very confusing. So we might need audio and video modalities to provide complementary information for us to make the decision. From this example, we can see that multimodal data, they enable the network to learn from an enriched representation space. And this is especially beneficial for those very hard examples. However, on the other hand, they also brings redundancy in computations for those easy instances that can be correctly predicted, maybe just using a subset of modalities or just using very simple fusion operations. Therefore, motivated by this, we present DIMM. It is an approach that adaptively fuses multimodal data. So compared with these static fusion approaches, DIMM can bring computational savings for easy instances and matches the representation power for hard instances. Now, let's dive into the designs of DIMM. So I will first introduce its decision-making schemes, considering two levels of granularity. first modality level DMM, which is a coarse level, and fusion level DMM, which is a fine grain level. Then I'll introduce its training strategies. So for modality level DMM, we design a set of expert networks along with a gating network, resembling a classical mixture of expert network. So here, each expert network is specialized for one or a subset of modalities, and we have a gating network that decides which expert network should be activated in a sample-wise manner. So the gating network will take multimodal features as input and outputs one hot vector to decide which branch to select for each instance. And in this way, the computations for the unselected expert networks can be saved. Next, let's discuss fusion level DMM. So we first present the design of a fusion cell. So the fusion cell consists of a set of fusion operations along with a gating network. For fusion operations, it can be implemented as any function to fuse multimodal features, such as very simple addition, or just using one modality and skipping the other, or some complex fusion operations, or transformer fusion. And for the gating network, like in every fusion cell, we also have a gating network. The gating network takes multimodal features as input and decides which fusion operation should be adopted in a sample-wise manner. So this is an example fusion cell with 3 candidate fusion options. With the fusion cell in hand, we now stack these fusion cells to build a dynamic network. And figure B here is an example dynamic network with 4 fusion cells and 4 extraction blocks for future extraction blocks for modality 1 and 2 here. And here we use a global gating network to provide decisions for all fusion cells for better integration. Finally, we are showing resulting possible architecture of our dynamic design. So if for fusion, like for some kind of input for fusion cell 1 and 2, we use the operation O2, and for fusion cells 3 and 4, we are using O1 as the operation, which means we just using the X1 modality. So this is a resulting architecture, and we can see that the gray boxes, the computations corresponding to these gray boxes are saved because we figured out, like after block 2, there is no need to process features from modality 2. We decide to only use features from modality 1. So the feature extraction blocks for modality 2 can be saved for some particular example. And in all, we can see that fusion level DMM provides us with ways to flexibly control the degree of multimodal fusion. We can now decide when and how we want this multimodal fusion is performed in a sample-wise manner. Next, I'll discuss these training strategies. So first, we introduce a resource-aware training objective. Besides the regular task loss, we have a computational loss term, which is associated with the computations of executing the selected expert network or the selected fusion operation. And this objective can allow us to achieve a desired trade-off between computational efficiency and performance. So the lambda here in the loss term controls the relative importance of these 2 loss terms. And we can flexibly adjust the value of lambda to target high accuracy or high efficiency based on our actual deployment constraints. Finally, about optimization, since the gating network provides discrete decisions, so we use Gamow softmax and reparameterization techniques to make the training of the gating network differentiable. And then we propose 2-stage training. So in the first pre-training stage, the goal is to make sure every pass of our dynamic network is sufficiently trained before the gating modules get involved. And then in the second fine-tuning stage, our goal is to involve gating network into the optimization process, and the whole network is trained in an end-to-end manner. As for the experiments, we select 3 different multimodal tasks covering different modality combinations. we use modality level DIMM for the first two classification tasks and fusion level DIMM for the more challenging semantic segmentation task. In terms of the result, we can see that so this is the two figures corresponds to DIMM performance on the first two classification data sets, and we provide variants of DIMM by controlling the lambda in the training objective. So we can see that it's very flexible and effective, achieving a good balance between computational efficiency and performance compared with the static unimodal network and the static multimodal network. And here is a result of fusion level DIMM on RGBD semantic segmentation task. We can see that it brings improved performance as well as reduced computations at the same time. Finally, we demonstrate the improved robustness of DIMM over a static multimodal fusion network. So we randomly inject Gaussian noise to RGB images or depth images or both modalities. And we vary the noise level and plot the performance curve along this process in the left figure. We can see that as the noise level goes up, the performance gap between DIMM and a static multimodal fusion network becomes larger. So this indicates that DIMM is more robust to noisy modality. And the right figure is some qualitative segmentation results. So we see that although for the static baseline EA state net, they can generate reasonable predictions on the clean settings, the first and the third row here. But its performance got significantly worse when we add noise to the depth or RGB images. So it corresponds to the second and the fourth row here. On the other hand, our DIMM is still able to generate reasonable segmentation results on both circumstances. Finally, to conclude, DIMM is an approach that adaptively fuses multimodal instances during inference. It brings reduced computation, improved performance, and robustness. Future directions include developing better dynamic architectures for multimodal fusion and extending it to different multimodal tasks. And thank you for your listening. I'm happy to take questions.
Okay, as usual, if there's any question you can really ask.
When you're using different modalities, what happens when the modalities are somehow contradicting to each other, or when one modality is uncorrelated to another modality?
Yeah, so we have a gating network to decide, like it's possible maybe the one modality is telling you this is a positive emotion, but the other modality is telling you the other way. And we are relying on our trained gating network to help to decide which is the path we should adopt.
Okay, maybe I can ask a very last question. So I guess you suppose all the modalities are kind of like temporally aligned somehow. So have you tried stressing the model with slightly non-aligned modalities or something like that, so that as the other question was suggesting, you have some contradicting input to the networks. I guess in that case the gating will somehow work as a hard gating function that selects one modality which is the correct one rather than the other.
Yeah, I think it's a good question. Like we could explore it in the future for unaligned modalities. Right now we are using paired multimodal data.
Okay, thanks. And let's thank the speaker again. We have a last paper for this session. I guess the presenter is online. This is paper number 9, exposing and mitigating spurious correlations for cross-model retrieval. The presenter should be Jae-Myung Kim, University of Tübingen. If you're online, please unmute yourself and start speaking, and you can share your screen.
Okay, then I will share the screen first.
Yeah, can you, we try to raise the volume maybe?
Oh, yeah. Do you hear me well now?
Yeah, much better now.
Okay, great. Okay, hi everyone. I'm Jae-myung Kim from University of Tübingen. And today I would like to talk about my work exposing and mitigating spurious correlations for cross-model retrieval. Yeah, so yeah, as probably everyone might know, the cross-model, especially on the text image retrieval task, considers the setting where the query images are used to retrieve the matching text from a text database and vice versa. So for instance, given a query like image showing two dogs playing a frisbee, for instance, we hope the retrieval model to retrieve the sentence that exactly describes the image. Like, so in this case, it would be two dogs sharing a frisbee in their mouths in the snow. However, what we observed is that retrieval models commonly learn to memorize spurious correlations in the training data, such as frequent object co-occurrence, for example, instead of looking at the actual underlying reasons for the prediction in the image. So for instance, here I brought the same example, two dogs playing a frisbee. And then what I did is that we like manually just removed the frisbee and then used this object removed image as a query image and then fed it into the model. And then the model actually retrieves the sentence that still describes the object that I removed. So here it will be a frisbee. And to further quantify this spuriousness of objects, we proposed the object decorrelation metric called ODMAP at K, which captures the model's robustness to semantically unrelated object correlations in the training data. So concretely, what we did is that we first synthesized an image. And how we did is that given, like, let's say we use the MS COCO dataset, for instance, and then given an image, we get the bounding box for each object, and then we randomly select one object and then remove it, and then inpaint that removed region using the inpainting GAN model. And then next, after we get the object removed image, we fed this to the model and then retrieved the sentence from the text database. And then if the retrieved sentence contains the word that we have removed, for instance, here, it would be a woman or a person, then we consider it as wrong. And if the retrieved sentence does not contain the object that is removed and just contains the object that exists in the image, then we consider that as correct. And then after we get the wrong or correct list, we measure the accuracy using the MAP at K, which was proposed in the ECCB test 2010. And here I've just brought some results tested on the existing models like BSE++, which uses CNN model, or the CLIP or BLIP model, which is a vision language models. And then if you look at the MS COCO ODMAP at 1 result, it's like near 50 to 60%, which means 1 out of 2 results are wrong, which seems like a lot. And then after that, as we can imagine, we wanted to mitigate this spuriousness. And what we did is to fine-tune the model. And to do that, we augmented the data set. So here, to fine-tune the model, we not only used the original data set X and Y pairs, so here X is an image and Y is a text. But also we also synthesized the image and text pairs called here I called it X prime and Y prime. So for the synthesized image X prime, it's same as I described before. But for the Y prime, there was a problem because actually it's quite difficult to make a sentence that exactly describe the synthesized image X prime. So we tried a lot of different kinds, and we found that removing the noun phrase chunks from the original sentence Y works the best. So for instance, if the given text is like there are two people riding horses near a body of water, by removing the noun phrase chunks here, so it will be a people or two people, then the synthesized text would be they're riding horses near a body of water. So sometimes this text, this synthesized text, is not a complete sentence. It's like it is grammatically wrong sometimes. But still, when we use this as an augmented data set, it actually worked well, which I will show you later for the results. Actually, right now. So as you can see here in this table, so if you look at the clip, for instance, compared to the clip fine-tuned model, which is just fine-tuning the clip model with the original data set, when we also use our synthesized data set for fine-tuning the clip, when fine-tuning the clip model, the spuriousness accuracy improved up to 70%, which is like about 10% different. And also in the BLIM model, for instance, it increased up to near 6% in the ODMAP at 1. And also, this actually does not harm the standard evaluation result. So we can see in this table that in the standard retrieval evaluation result, compared to the fine-tuned version, our method works on par or works better compared to the fine-tuned one. And lastly, I brought some qualitative results. So for the first example, I brought some image that the food is removed from the dish. And when I gave this food removed image as a query to the clip model, the clip model actually just retrieves the sentence that describes the word, that describes food. But in our case, it's just describing the dog and not the food. And it happens the same in the person's case. So when I remove the person in a tennis court, the clip model still retrieves the sentence that describes like woman or athlete. But in our case, it's just describing the tennis ball or yeah. So in conclusion, we found out that existing models tend to retrieve samples based on cues that might not be semantically related. So to mitigate this issue, we trained the model with augmented synthetic data. And also to quantify it, we proposed a new object correlation metric called ODMAP at K, which measures how well the model retrieves samples based on the right cues. Yeah, so thank you for listening. And yeah, please feel free to ask questions.
Thank you very much. It was very interesting. Any question from the audience? Yeah, you should probably come over and see if yeah.
Okay, so thanks for your talk. What I was wondering, I think it's definitely sound to do object removal and to see how to decorrelate in the training phase. But the removal of objects in the images always causes some kind of artifacts. And these artifacts are also learnable, and there are lots of examples about this in the literature. So do you think the network has really learned that there's no object there, or does it learn these artifacts of removal?
All right. So actually, that's a good question. So we also considered like that a lot. So when we remove the objects like in a normal way, like just making it as a black color instead of inpainting, it's actually really moving the data to the out of distribution data. And when we use the inpainting, for example, it will like make it closer to the in distribution, but that doesn't mean probably that it's not exactly the in distribution. So that's why we tried not only to see in the spuriousness metric, but also on the standard evaluation to see if it decreases the performance. So if it's really out of distribution and use it in the training data set, probably it will much harm the results in the standard evaluation. But when we use the inpainting GAN, it actually didn't happen. So yeah, I mean, yeah, so I cannot say that we like totally addressed that issues, but we were also considering that, and we found out that probably the inpainting GAN was the best to try to mitigate the issue.
Okay, so if there's no other question, I think we can thank the speaker again.
Yeah. Thank you.
And we will be back at 3:15 after the coffee break with the oral session number 3.
Guys mind if I just set my computer?
Now let me see if this is fine. You just need to share it. Share this one. Share. I don't have a clue if you're sharing the right one, but
It looks good.
it looks good, right?
Yeah.
But as usual, Zoom doesn't, I don't know if, yeah, I think we can start, right? Okay. You are in one.
Yeah.
Okay. Okay. Okay, we'll start again. Hopefully I started everything with the last oral session. So we have the paper that will be presented by Yin Wang, and the title is Adapting Crowded Visual Question Answering Models to Low Resource Languages. Floor is yours.
Thank you. In the past few years, we've seen many breakthroughs in vision and language tests, leveraging pre-training on large image and text data sets. However, these advances have been restricted to the English language only because we don't have such large and high quality data sets for other languages. To address this gap, XGQA is proposed as a multilingual evaluation benchmark for the VQA test, extending the test time split of English-only GQA data set to 7 typologically diverse languages, including German, Portuguese, Russian, Indonesian, Bengali, Korean, and Chinese. An example of the data set is shown in the image on the right. As we can see, the input is image and the question in the target language, and the output is the answer in English. However, XGQA is only for evaluation purpose, so we don't have a training data set for multilingual VQA. Therefore, many previous works use machine translated data to solve this issue. It is a cost-efficient approach to obtain large-scale multilingual VQA data because we can directly use softwares like Google Translate. However, there are some shortcomings about this approach.
The first is that the resulting model performs much worse on languages that are not included in the translated dataset, which is not surprising. Secondly, it depends on the quality of machine translation, which is still highly reliant on the availability and quality of resources in the target language. So still, it puts the languages with low resources at disadvantage. Lastly, trains a model from scratch doesn't fully exploit existing large-scale pre-trained English BQA models. To solve these issues, we propose a new method that extends existing English BQA to multilingual setting. Because the only thing that is different here is the language. So we just need to replace embedding layer and insert adapters to the text encoder while we can keep other parameters frozen. In this way, we can decrease the training time, and also we can preserve the BQA ability of the original model. The base model we are using here is MDitor, which is a English BQA model. It is an end-to-end text modulated detector that is trained to predict bounding boxes with alignment to object phrases in the query text, and is fine-tuned for BQA using the GQA dataset. As we can see in the architecture diagram, they use encoders separately. So they use two independent encoders to encode image and text, and then the image features and text features are projected into a shared embedding space and concatenated together. In the end, they are fed into a transformer to predict the bounding box, the question types, and the answers to the questions. And we call our model XMDitor as the multilingual version of MDitor. And the magic only happens in the text encoder here. To update the text encoder, we have three objectives. The first is MLM objective, which is very natural because we want to learn the new representation for new languages. And we train the text encoder using the OSCA dataset, which is a web scraping dataset for different languages. The second one is code switch QA. Code switch here means replacing a proportion of words in the original English text with its translation in the target language from a bilingual dictionary. So an example is on the left. As we can see, the original English question is, what color is a sofa? And we randomly replace 50% of the tokens by its word level translation in Chinese. So here, color is replaced by its translation in Chinese. And this is very cost efficient because everything is in word level, and we can easily obtain bilingual dictionaries for all languages in the world. However, the shortcoming of this approach is that sometimes it is not very satisfying because it doesn't consider the difference in sentence structures of different languages. The third objective is contrastive learning. Also, we don't have multilingual BQA dataset. We do have image caption dataset for some languages, such as Chinese and German. So for this kind of languages, we propose the following contrastive learning objective. In the peer, we have three entries. The first is the image, the second is the English caption for the image, and the third is the caption for the image in the target language. Note that the new caption is not necessarily the translation of the English caption, but since they are describing the same image, we assume they're similar and they should have similar embeddings in the embedding space. So we compute the influency loss between the image and the English caption, the image and the new caption, and the influency loss between English caption and the new caption. So this table summarizes the experiments for different configurations that I just mentioned. So configuration A and B is just updating embedding layers with MLM loss. And the performance is not good. As we can see, the average accuracy is 12%. And in configuration C, we add a code switching strategy. And this improves the performance from 12% to 21%, which is a large improvement. So code switching QA is very effective here. The configuration D is inserting adapters to the text encoder. So in this way, we allow for more flexibilities when modifying the text encoder while not increasing the training time too much. In the end, we add contrastive learning for German and Chinese because they're the only two with the image text data sets. And this further improves the performance by 3%. In addition to the zero-shot cross-lingual transfer, we also add few-shot cross-lingual transfer following the original setup as XGQA. We fine-tune the previous checkpoints using 5, 10, 20, 25, 48 images with their corresponding questions and answers. And the results are shown in the bar charts here. So the green ones are our method and the yellow ones are our method plus contrastive learning. So they are only valid for German and Chinese. And as we can see on Bengali, Indonesian, and Portuguese, we outperform existing approaches and our results are also competitive for other languages. So besides the quantitative results, we also provide some qualitative examples. One advantage of our approach is that we provide bounding box, which makes our results more interpretable. Because our original model MDitor had this functionality, so we also have this as our advantage. So as we can see, for example, for the Portuguese, it successfully identified the zebra in orange bounding box and the vehicle in blue bounding box. And all the languages have the correct answers, but some of them may fail to predict the correct bounding box and the spans. So for example, here for Indonesian, D, we can see it predicts the wrong zebra tokenization, which might be an issue of the tokenizers. Okay, in conclusion, in this paper, we propose a novel method to adapt the SOTA grounded VQA model MDitor for low resource languages without using any translated data. Our method integrates multilingual uni-model training with MLM objectives and multilingual multimodal training with QA objectives with code switch data and contrastive objectives with multilingual image caption data. And we use adapters for training. And in the end, our model is also able to produce bounding box, which is able to provide more insights into the reasoning process of the model. Thank you.
Thank you. Do we have any questions from the audience? Maybe I can ask something. I checked with I remember must work, but I don't remember if you did some ablation about the amount of text that you can have. I mean, what is the, let's say, the advantage of using your method, right? When you have very little text of a certain language, right? And going down to very little amount of text. Do you have such an experiment?
Oh, do you mean for the MLM objectives?
Yeah.
Yeah, that's a good point. So actually for the OSCAR data set, different method, different languages have different data size. So for example, for Korean, I remember the data size is much smaller than Russian and Chinese. So I use 100K updating steps, which means I need to like go over more epochs for languages with fewer resources. Yeah, and yeah, I think like in this way, I think the training performance is worse than languages with more resources. Yeah.
Yeah. Okay. Any other question? Yeah.
I was curious about so for the languages that you consider in the paper, we do have other kind of text-to-text correspondence available. So I was curious if you tried distilling the English model with maybe like an excellent Roberta or MD Roberta model. And so how does this method compared to those methods where you are distilling but on an entirely different parallel sentences data set?
Sorry, do you mean compare the model to other multilingual VQA models?
Well, I mean, you have a large English
Mhm.
data set. And so taking that English text featureizer and using that as a target to train a multilingual embedder. So in the multilingual embedder, you can pass text in lots of different languages, and then you use a different, like not necessarily related to this problem, but other sort of English to the standard language translation data sets to maybe update multilingual text pattern.
So you mean using machine translated data set to update?
Yeah, just the text featureizer. How much like what's the kind of gold standard if you had that machine translated data set?
Yeah, so it is actually explored in previous work because they use a large scale machine translated data set to do the update for the text encoder. We didn't use machine translated data set because we think it do have some shortcomings, and the training is much longer than like of just fine tuning a pre-trained English model. Yeah, and also if we use machine translated data, I think a natural question is why not just using a like translated questions as the input? Yeah, and this is also compared by this previous method like UC2, CCLM, TD, MML. And I think if I remember correctly, CCLM report that they all perform directly using translated input by like a small portion. Yeah, I think like it's also interesting to use machine translated data, but in the meantime, I think we should also explore methods without machine translation.
So you tested a different paradigm somehow, right? And you didn't want to just start from something like what he said, right? So you just wanted to switch it completely just to see how it works.
Yeah,
right?
yeah.
Okay, thank you.
Close it. Okay.
Thank you.
Thank you.
Okay. Okay, so we have the second speaker. Asmar Nadim, are you online?
Yes, I am online. Thank you.
Yeah, I think you are online, but I cannot hear you.
Can you hear me now?
I can, yeah, my fault. I have the volume very low. Yeah.
All right.
Give me a
Thank you
second.
very much.
Give me a second. Try again. Okay, so Asmar and Nadim will present the paper named Same Pause, Grammatically and Semantically Correct Video Captioning. The floor is yours.
Thank you. So I'm going to present our work on video captioning, which was done while in partnership with BBC and EPSRC. So this work is part of AI for Me project, where we are working on personalized media experiences. SAMPOS is basically a visual language model for video captioning. It is a supervised method without any pre-training stage. In this work, we are trying to generate captions which are grammatically and semantically correct at the same time. And also we achieve state-of-the-art performance in this category on MSVD and RVTT benchmark datasets. So what is video captioning? It is basically retrieval of video through text by automatically recognizing the objects and the actions within a scene. Prior approaches usually focus on generating captions either word by word, or they try to formulate the sentence in the form of actions, which are basically the predicate or principal objects, which could be like physical entities. So because these objects are usually physical entities, so they miss key information, and also the grammatical structure is not there. So we basically focus on three challenges. So how to align visual and linguistic information such in a way that it is grammatically correct. Second challenge is basically how to add the fine grade information so that the caption is semantically correct as well. And then obviously in the next stage, we have to fuse this local and global information such that it is the caption generated is grammatically and semantically correct. So in our method, we basically propose 4 parts of speech-based blocks, which are basically determinant plus subject, auxiliary verb, verb, and determinant plus object. And then we fuse these linguistically and visually aligned features from these 4 blocks in a global local fusion block, and then the caption is generated word by word. So why we use these 4 POS blocks? So when we did analysis of the captions, the ground truth captions of MSVD and MSRVTT benchmark datasets, we find out that these 4 combinations or the parts of speech are highly represented within the captions. Because of these this analysis, we use 4 POS blocks. So in the Sampos architecture, we have a visual input in the form of RGB frames. And these are passed through 3 encoding networks, which are basically the object features, the 2D features, and the 3D features. In the next stage, we have visual feature masking for the 2D features and the 3D features, which basically introduces robustness or generalization in the network. In the next stage, we then pass these features through 5 blocks. 4 blocks are basically the POS blocks or the parts of speech blocks, and then these 4 features are then combined in a global local fusion block. Then these are passed to a caption block, then which generates a caption on a global level. The supervision is done in all these blocks. So this is done through Roberta encoding, and then the overall loss is basically the verb loss, the determinant plus subject loss, plus the auxiliary verb, determinant plus object, global local fusion block, and the overall caption loss. We haven't used any separate gains for these losses because the number of losses are too many. So even if we apply, there isn't much difference. So we just used 1 as the gain for all these losses. So in terms of evaluation metrics, all the state-of-the-art or the previous prior approaches use these 4 metrics: B@4, Meteor, ROG, and CIDR. So B@4 is basically an n-gram based metric, which usually you look for matches between the predicted and ground truth captions. Meteor is a recall based metric. It looks for word-to-word alignment between the predicted or the generated and the ground truth caption. ROG, on the other hand, looks for longest common sequence of shared words between the predicted and the ground truth caption. CIDR is a robust metric which basically looks for the semantic meaning of captions, so that it looks for basically the cosine similarity between generated and ground truth caption. Obviously, these 4 metrics are not good enough to predict the grammatical correctness or measure the grammatical correctness of the generated captions. So we introduce a new metric, based on the perplexity score. We use GPT-2 pre-trained model for measuring the grammatical correctness of the generated caption independent of the ground truth. So in terms of our results, so our method improves on the state of the art on both MSVD and MSRVTT benchmarks. In terms of MSRVTT, our method improves around 3%. In terms of MSVD benchmark, in terms of CIDR, our method improves around 4%. In terms of the GS metric, which we introduced, which is the grammatical correctness, our method improves around 10% on MSRVTT and 16% on MSVD. So in terms of qualitative results, our method, as can be seen on the first two rows, right side, like SAMPOS is our method and HMN is basically the state of the art. So in the first example, a man is riding a motorcycle on the road. State of the art is like a man is riding a motorcycle. Ground truth, a person is on a motorcycle on the street. So basically, in the second one, people are playing football. State of the art has same caption, but ground truth is people are playing sports. So our method introduces fine-grained details. On the other hand, the grammatical structure is intact. The other three examples basically show that our method is not only semantically correct, but also grammatically correct. So in the second row, left side, a woman is applying makeup on her face. That is basically our caption. And then HMN, which is state of the art, is a woman is applying makeup. Ground truth is there is a cute woman is applying makeup. Similarly, in the last row on the right side, you can see a woman is walking down the street. That's the caption generated by SAMPOS. Then the state of the art, there is a woman is walking on the street. Ground truth is a young woman rushing through a couple of places. So our method has fine-grained details, and also the sentence structure is grammatically correct. In terms of ablations, the first 5 rows show the contribution of the added blocks. So without determinant plus subject, the effect is clearly seen. And then obviously the verb, auxiliary verb, determinant plus object, and global local fusion block. So this one is basically the visual feature masking, which introduces generalization. Because of it, there is around 0.5% improvement in MSRVTT on CIDR and around 4 to 5% on the CIDR metric of MSVD. The other 3 components, which are basically adverb, adjective, and conjunction, these are not highly represented in the captions of MSVD and MSRVTT when we add these. So basically, they actually adversely affect the performance. And the next 2 are basically with subject and with the object only. So if we don't add the determinant with the subject and object, the performance is not good enough, which means that determinant actually helps in deciding whether the subject and object are singular or plural. With all means that if we add the 3 less represented POS blocks with the other 5 blocks, then the performance degrades as well. Conclusion, so we have introduced 4 POS blocks and a global local fusion block, which helps not only in adding fine-grained details to the semantic correctness, but also help in achieving a grammatically correct sentence. On the other hand, visual feature masking improves the model performance and adds generalization across distributions. In the end, SAMPOS captures fine-grained details and advanced video language alignment and understanding research. That's all. If you have any questions, please let me know.
Thank you. Do we have any questions from the audience? No, so maybe one from me. Have you detected some limitations of your method comparing to state-of-art methods? What is your opinion, I mean, on this?
So in terms of limitations, particularly the MSRVT dataset has multiple events going on at the same time. So our method has this limitation that it cannot generate a caption which comprises multiple events. So that is something we want to work on in the future. The other thing was that, for example, we haven't added all the POS blocks. That is an advantage in a way, but for example, if there could be a dynamic structure of the model, like, you know, we have predefined blocks right now, but if we could do that in the runtime, that could be that could add some kind of robustness. Yeah.
Okay, thank you. Any other question? Okay, let's thank the speaker again. Thank you.
Thank you.
So the last talk, the last oral for today is Ingma.
Yes, I'm here.
Hello. Okay. So he will present the paper named Robust Multi-View Multi-Modal Driver Monitoring System using Masked Multi-Head Self-Attention. So the floor is yours.
Okay, going to share the screen.
Yep.
Okay. Hello, everyone. My name is Yiming from the University of Warwick. So today, on behalf of our collaborators from Warwick, for the Motor Company, and the University of Glasgow, I represent our paper, Robust Multi-View Multi-Modal Driver Monitoring System using Masked Multi-Head Self-Attention. So the first question you may ask is, what is a driver monitoring system? You know, nowadays, the technology of self-driving is advancing very fast. But sometimes this kind of technology is still can be still immature to be applied in the real world scenarios, and this technology can cause some problems like unwanted or controversial accidents. So the ideal scenario for this technology is still like we still let the driver to have the full control of the vehicle, and we use some smart systems to monitor the driver's readiness level for driving, and we intervene if necessary to, you know, just hand over the control to the self-driving system to improve the road safety. So as this diagram illustrates, the driver monitoring system can take multimodal data as input and leverage some machine learning algorithms to estimate the driver's readiness level for driving. As for the modalities, there can be many different modalities used in modern driver monitoring system. The most commonly used ones are RGB modalities, the depth modality, and the infrared modalities. These three modalities are captured by cameras, and these cameras can also be deployed at different locations in the car to monitor the movements of different body parts. So for example, the cameras on the top can monitor the driver's the movements of the hand. So as these two pictures illustrate, and the cameras in the front of the driver can monitor the movements of the upper body. So these you know, different view cameras can have different focuses, and also sometimes the ECG can be employed to monitor the heart rates. You know, when the driver feels fatigued or anxious, the heart rate can change very fast. And also the audio of the driver can also be monitored to see whether the driver is speaking to the passenger or talking on the phone. And these distractions can cause accidents. So it's kind of important modalities. So in a word, modern driver monitoring systems are multimodal and sometimes can also be extended to be multi-view. And the research of driver monitoring systems can incorporate a lot of domains. And in this paper, our work specifically focuses on driver action recognition, which involves classifying the driver's action into normal driving and several other non-driving related activities, such as texting and drinking. And our paper well, in short, our contribution in the paper have threefold. So for the first, we proposed a novel method to handle modality fusion. And we also manually annotated the anomalies in the DAD dataset. So here the DAD stands for driver anomaly detection. So as you can see, it has an anomaly detection inset. But one thing unusual for it is it also have anomalies available in the training set. So we decided to manually annotate the anomalies in the training set and also the test set so that we can conduct multi-classification of drivers' activities. And we've also done a lot of experiments on our enhanced DAD dataset. And the results shows that our proposed method can achieve the state-of-the-art performance. And also, when trained with a large random masking ratio, our method is robust against modality or view collapses. And here are the related works. And for the time considering, I'll just skip it. And for the method, and here is the overview of our proposed method. As you can see, it's very straightforward. It's very simple. So for the input video clips, we use a 3D ResNet to extract spatial temporal features, and then we input these features into multi-head self-attention mechanism to learn the relative importance or to learn the interaction of different modalities, and then we feed the fused feature to a multi-layer perception to generate the probability distribution of each class. And for the multi-head self-attention fusion module, here is the diagram of it. So it's very simple. It's just like a vision transformer. The first step is tokenization. We tokenize the input of extracted features, and then we add the positional embeddings. Here, the positional embeddings are spatial temporal. And another difference is we also need to add the data source embedding so that later the transformer encoder can know which data source each patch was originally from. And we randomly mask a large ratio of the patches and feed the remaining patches into the transformer encoders. And we sum the output to generate the fusion method. Because this area is quite new, so there's not much work to compare against. So we also compare our fusion method with some other straightforward fusion methods, like summation or 1D convolution, or using some other attention mechanisms like squeeze and excitation or attentional feature fusion. And here are the experiments. So basically, the data set was proposed 2 years ago, but there's not much work on it. So this one was the original paper that the data set is based on. It was based on decision level fusion, and these ones are feature level fusion, and the last one, MHSA, which is short for multi-head self-attention, is our proposed method. So as you can see, basically our proposed method outperforms the rest on each scenario, and also our proposed fusion method is effective for each fusion, for the fusion of each modality or each views. That I mean, our model can always benefit from having more views or modalities, so the performance can always improve. This table here, this illustrates the AUC ROC score for the non-driving related activity detection task on the DAD dataset. And here for the multi-class classification of drivers' activities, this table illustrates the mean average precision scores. And here this charts demonstrate we visualize some scenarios in the test set. So from the left-hand side to the right-hand side, there are 4 data sources. The first one is front IR, front infrared, and the second one, this one, is front depth. This one is top IR, this one is top depth. And the text here illustrates the prediction and the corresponding confidence of falling into such a class. So for the first two, apparently the driver it's either adjusting the radio or drinking, and our model can predict it precisely with the probability of 82.8% and 81% respectively. And for the last case here, the ground truth is actually talking on the phone, but from the middle frame of the input video clips, we cannot see that there is a phone shown in this case. So our model predicted with the wrong label that is talking to the passenger with a relatively low confidence. And this kind of scenario is quite common in the data set. So we think the data set, since the data set, the video clips is quite untrimmed. So we think maybe in the future work, we use weakly supervised learning, for example, multiple instance learning can better fit this scenario. And for the last one is the robustness analysis against the modality of view collapses. So we train our proposed method on the 4 data sources, but with a varying random masking ratio from 0 to 0.9. So 0 means all the extracted feature patches are inputted to the transformer encoder module, and 0.9, that means 90% of the patches are masked out. So the input is only left at 10%. And we evaluate our model on each modality of view collapse scenario. So for example, when one modality of view is collapsed, that means there can be like a top IR, top infrared, or top depth, or front IR, or front depth. So there can be 4 different scenarios. We evaluate our model's performance on each of these scenarios, and we take an average. And for these 2 charts here, the x-axis stands for the random mask ratio, and the y-axis stands for the score measured at the different metrics. So the first metric is the multi-classification accuracy, and the second metric is more suitable for imbalanced classification, which is mean average precision. So given each x, that means given each fixed random mask ratio, the gaps in the y-axis stands for the degree of the performance degenerates. So if the gaps between these points are large, that means the performance degenerates quite significantly. Well, if the gaps are smaller, that means the performance is not very severely degenerated. So the conclusion is very straightforward. When training the model with the large mask ratio, the resulted model is more robust against the modality of view collapses. So basically, that's all. Thank you.
Thank you. Yiming, are there questions from the audience? No, so maybe it's a curiosity. But what makes what this task has different what are the difference about this task from traditional action recognition, right? You propose this on drivers, right? Drivers' behavior, something like that.
So traditionally, do you mean for driver action recognition or for some general action recognition?
Yeah, what's the difference? Why this is really worth it of attention?
That's because I can refer to some related work. So originally, the driver action recognition was only single view and a single model. So for example, as this image illustrates, so using a single modality and a single view can have some limitations. So for example, this one, the modality used is RGB modality. And as you can see, it's not very robust against illumination changes. So you can see this gentleman's face is covered entirely in the shade. So we cannot monitor the movement, for example, the gaze of the driver accurately. And also from a single view, in this scenario, the driver is texting with the right-hand side, but what if the driver is actually texting with the left-hand side and with the right-hand side on the steering wheel? So there is a possibility that some parts of the body can be blocked by the single view, can be blocked by either the other parts of the body or some other decorations in the car. So sometimes single view cameras cannot function very well. So that's why we need to use multi-modal and multi-view cameras to monitor the driver states. And also for the previous multi-modal, multi-view driver monitoring systems, most of them are either based on decision level fusion or input level fusion. Our work is the first that studies different fusion strategies at feature level fusion. We think this is quite important because for input level fusion, these just simply concatenate all the input clips, and sometimes there is an inconsistency between different views. So simply concatenate them together is not a very good strategy. And for the decision level fusion, because what they are fusing is the scores instead of the semantic features, they cannot fully utilize the complementarity between different views and all different modalities. So we think fuse the features from we think modality fusion from the feature level is the most is worth of our attention. So that's what our work is focused on.
Okay, thank you. Now, so let's thank the speaker again. So let's get to the final. Are you for the final keynote? Yes. Are you going to? Okay.
Okay, so we have the last invited speaker before the poster session, and he's Alex Oniski, and Alex the bachelor degrees at the University of Illinois Urbana-Champaign, and he made a PhD at the University of Washington, working with Oniski, Brian Carles, and Steve Seitz. So I suppose in 3D computer vision. And now he's working in Google Research, he's a research scientist in Google Research, and also a postdoctoral scholar at Berkeley, working with Alyosha Efros. So he's
Okay, cool.
okay.
All good? All right. So I talk notoriously loud, so just bear with me. If it's a bit too loud, let me know. I'll get further away from the mic. So thanks for the intro. Just very quickly about myself at Google Research scientist, postdoc at Berkeley. So I just want to start off my talk by taking a quick second to appreciate just for a second how great these diffusion models have gotten. I mean, these past couple of years have been, a roller coaster ride in the space of generative models, and especially for image generation. I mean, just like, look how far we've come. These are all generated images using Midjourney. And, sometimes these generated images look so good that I can't even tell that they're fake. And I've been using these models a ton, training them, but also just using them to be creative. And in fact, I should probably confess that I actually had a bit of a hard time finding a good portrait photo of myself to use for this talk. So I actually just trained a model to generate one for me. You know, probably for most purposes, this is fine, but my friends would tell you it doesn't look exactly like me. Anyways, the title of my talk is Language Grounded Visual Manipulation. And this talk will cover about 4 or so recent papers that we've worked on in the space of image and 3D editing, semantic manipulation, and a bit of diffusion model explainability. So let me start off by first offering a high-level motivation for some of the work that we've been exploring. So as I said, it's super impressive that you can generate just about any image that you can describe, right? And this has been transformative for digital artistry. You know, whether it be for creating a final piece of art or simply for inspiration, the creative process can now be simplified to the following steps. First, describe the picture that you're imagining in your head, you know, or maybe even an abstract idea that you can't even picture. You know, give it to the model and you'll get an image as output. And of course, there's a pretty good chance that it won't be perfect, but you can repeat this process as many times as you need, gradually adjusting the prompt to contain more specific details that point towards what you're imagining and get new images as output that are closer to what you wanted. And this process usually repeats a few times over, refining your prompt once or twice or 3 or even more times until eventually you get something that's more or less good enough. And while this process can be very effective, I'd like to argue that there are a couple pieces of the usual creative process that are missing here. And in particular, I think the first and the last 10% are missing. So maybe you get to this image and it's good, but it's not exactly right. Maybe you wanted the composition to be slightly different, changing the size and the shape of the object, or maybe the colors weren't entirely right. Or maybe there were pieces of the image that you generated earlier that were good, but you wish you could stick them into this image. Well, right now, you can't do most of that stuff with these models because they're guided by only text. So we're still missing this last 10% of like tweaking or what we might call manipulative edits. Things that are closer to what we can do with traditional image editing tools and are crucial for getting something that's exactly what we want. And also, maybe we didn't want to start from scratch. Maybe we had a really great image that was almost right, and we wanted to start iterating from there. So most of these systems don't really make that process easy either. And finally, this loop of having to repeatedly change your prompt with magic words which correspond to the underlying latent space of image appearances is not really a great interaction paradigm. You know, we'd ideally want something which has a more intuitive user experience. And so in this talk, I'm going to cover a few recent papers that we've worked on to help fill in these gaps. So a super quick teaser. These are the 2 papers. The first one is called Instruct Pixapix, which is focused on image editing with natural human instructions. And then there's diffusion self-guidance, which is a mechanism for guiding images to satisfy certain spatial or appearance properties. Basically, it's a way of enabling a lot of the manipulative edits I was just describing. And then if I have time, I'll also cover a couple of other recent related works like Instruct Nerf to Nerf, where we applied some of the same diffusion-based editing methods to the 3D setting to enable instruction-based editing for captured Nerf scenes. As well as this recent paper called Diffusion Hyperfeatures, where we show that these diffusion models actually have a pretty good signal for extracting pixel correspondence between both the real and generated images. Okay, so I'll start off with this first project, and this was done at UC Berkeley with Tim Brooks and Alyosha Afros. So we called this project Instruct Pix2Pix, riffing off the title of the original image-to-image translation paper Pix2Pix, but of course, this time with instructions. So the pitch of the paper is basically, we've captured or we've downloaded an image, something that's an objective observation of the real world, but maybe it wasn't exactly the image we were hoping for. Maybe we were imagining something a little bit more magical, maybe a bit greener with some bluer skies or something like that. So what's the easiest way to get from what we have here to what we're imagining? Well, the easiest way that I can think of is to have, a best friend who's a Photoshop expert. Have this person sit next to you and just describe to them the things that you want to do. That'd be pretty natural, right? So we were hoping to build an AI version of this same experience. Effectively an AI that you could have a natural conversation with and would understand instructions for how to edit images. So here we can tell the AI, could you make this image look more like springtime? And it'll send us back the corresponding edited image. And so a couple of years ago, this might have seemed like a really far-fetched idea, but as of late, there have been a ton of cool papers that have, shown pretty phenomenal image editing results. And I'm sure you've already heard from some or most of these, but I'll quickly review some of them to put them in the context of our overarching goal. And feel free to stop me if there's some really pressing questions or something goes wrong with the slides. This was maybe put together in the past few days, so I'm not sure if the animations will quite work out. So for the most part, these methods are using diffusion models. So there's Dream Booth, which doesn't quite pitch itself as image editing, but rather it's like instance learning and manipulation. So it'll fine tune an existing pre-trained diffusion model to learn the concept of a particular object, like someone's pet. Such that it can manipulate that object and put it in different contexts, different scenes or different poses. Then there's Imagic, which has a similar fine-tuning scheme, but it's specifically for image editing. So you give it an image and you give it a target caption, basically a description of the full output image that you're hoping to generate, and it'll do some amount of fine-tuning of a pre-trained diffusion model so that it can produce that final image. And another example is prompt-to-prompt. And this solves a slightly different problem. So if you ask a diffusion model to produce 2 images for you, because of the way diffusion models work, there's really no guarantee that similar prompts, even with a single word or a single letter changed, will produce similar images. So here you can see we've changed the word bicycle to car, and it's entirely changed the structure of the image. It's changed the identity of the cat, it's changed the framing, the pose, and everything else. And so prompt-to-prompt sort of shows a solution to this, where it allows you to generate a pair of corresponding images from a diffusion model, given a pair of prompts. So effectively, it's a way for editing generated images. And the way that it works is pretty clever. So these big units that are used by these diffusion models have a ton of attention operations inside of them, including things like self-attention between patches in the image, as well as cross-attention between image patches and text tokens. And so over the course of inference, this network has a few intermediate byproducts, and in particular, it's these attention maps that I'm showing at the bottom here. And these broadly correspond to the structure of the underlying scene that's being generated. And so what prompt-to-prompt does is it produces one image like this one, a furry bear watches a bird. And when it goes to produce the second image, say a furry bear watches a cat, it'll borrow the attention maps from the previous run and just inject it into the UNet instead of computing it from scratch. And there are a few parameters that can be tuned here, like how many of the attention maps are borrowed or at which stages of diffusion, so on. But in any case, this ends up producing 2 synthetic images that are basically in correspondence aside from the changes in the text prompt. So these methods all work very well. And certainly compared to what was available to us a few years ago, it's entirely mind-blowing that some of these things are even possible. But none of them quite do exactly what we were hoping for, which was, again, motivated by this text message conversation. Our objectives are, this method should work on real images, not just generated imagery. We want to be able to interact with this editor naturally, by giving instructions for how to change the image in natural language without having to describe, the full image, or without having to offer a mask of the things we're trying to change, and without having to offer multiple images of a particular object. And finally, we want this editing process to be interactive. We want to feel like somebody's sitting next to you that you're interacting and iterating on your image with, having a short feedback loop that can allow you to tinker and try new things. And this really means that we don't want to rely on extra inference time processes like inversion or fine tuning. And so in short, spoiler alert, our method does these things, and I'll go through a quick gallery of results before jumping into the technical details. So here's the teaser result. You can see we are able to swap the sunflowers with roses in a Van Gogh. We can do contextual edits, like find where the fruits are in this top right example and replace it with cake. We can turn Woody from Toy Story into a real person. We can replace the jacket with leather and so on. So here's another example. This is a girl with a pearl earring. You can turn her into anime, into James Bond, make her sad and so on. And here we have the iconic Beatles Abbey Road album cover in a whole bunch of different styles, like, underwater in Hong Kong, Minecraft, and so on. So how does this work? Well, so no surprise, we use a large diffusion model. And the model takes as input an image and an instruction, and we train it to produce the edited image. And we treat our problem as a supervised learning problem, where we basically collect a large data set for this particular task. And the data that we need for this is a text image pair as input, which is an input image and a text editing instruction. And as output, we want an image, the edited image. But the big question is, where do we get this data? It's pretty infeasible to get hundreds of thousands of examples from such of these types of edits from artists. And this isn't the type of data that you can easily find on the internet. So what we decided to do instead was to generate this data set. And we do this by combining a large language model and a text image model. So we already have models that can complete text or edit text like GPT-3 or ChatGPT. And we have models that can turn text into images like any of the text to image models that we've all been using. But we don't quite have a model that can create the exact triplet of data that we want. But you can kind of imagine by looking at the top two here that there's probably some kind of high level arithmetic that you can do between these two things to produce exactly the data that we want. So let me tell you how we did it. So we start with the problem grounded entirely in text. So forget about the images for a bit, and let's just focus on the problem of editing image captions. So the same thing as before, where we have an input, an editing instruction, and an output, but in this case, the input and the output are just text descriptions of images. So that's an input description of an image, a text editing instruction, how we'd change the image, and a new description describing the output image we'd get if we perform that edit. So this is a text-only data set, and therefore a large language model like GPT-3 should be able to handle generating something like this. And in fact, it does. So we worked on this project before things like ChatGPT were around. And so we were using here GPT-3 in the OpenAI playground. And if you look here, you can see that if you give it a handful of examples where you've described an input image, an edit instruction, and an output image, it can learn to perform this transformation. So for a new description at the bottom here, landscape photograph of a lake with mirror-like reflection, summer green trees, and a given edit instruction, change the season to autumn, we can see that it produces the output description, landscape photograph of a lake with mirror-like reflection, autumn leaves. So it makes the edit appropriately. And even more, if you give it just an input description, like a young man with brown hair wearing a green backpack, it can actually generate both of the outputs for you. Like it can generate an edit which says, give him a blue backpack, and an output caption that says, a young man with a brown hair wearing a blue backpack. So pretty cool. It can be pretty creative. So we use this process that I just showed with GPT-3 to generate a massive data set of 450,000 examples that contain the triplet I just described: an input image description, an editing instruction, and an output image description. And so we actually do this by fine-tuning a pre-trained GPT-3 model to perform this specific task. And we fine-tune on a very small data set of about 700 handwritten instructions that Tim and I wrote over the course of a week, which, by the way, is not a very fun time. And then we perform inference. In other words, we generate examples for this data set by grounding the input caption on real image captions from the Lion data set, which is what Stable Diffusion is trained on. And so these are real captions for images on the internet, but we only use the captions and we don't use the images. So here are some examples from that data set. So at the top, you can see a couple examples of the ones that we wrote, like change the background to a city, or input is painting of a forest and pond, edited by without the water becomes painting of forest. And on the bottom, the generated ones are similarly creative, like asking for oil paintings in the style of a coloring book, or adding a giant red dragon to the great elf city of Rivendell, or making Kate Hudson look like a zombie. So now we have three pieces of text, the input Lion caption, a generated instruction, and the edited caption. But still, we're one step away from getting our final data set, which again was going from an image and a text instruction to another image. And so for this, we can revisit prompt to prompt. And we can feed in our two captions, the input and the output caption, to generate a pair of corresponding images. And this is what leaves us with our final data set, which is triplets of input image, output image, and text editing instruction. So here are a few examples from our data set, but overall, it's about 450,000 examples large. Okay, so now what's actually left is to train our model. So fortunately, at this point, it's a supervised learning problem, so it's relatively straightforward. And so to maximize generalizability, and the quality of the generated imagery, we start off with a pre-trained Stable Diffusion model, and we fine-tune from there. But unfortunately, as I'm sure most of you know, Stable Diffusion isn't trained for this task specifically, right? It's trained to turn a text prompt into an image. So we have to adapt the architecture to support our application. And so what we do is very simple. We simply concatenate the input image along the channel dimension of the first layer of the UNet, and we initialize the corresponding weights to 0. And for the text instruction, we pass it through the usual spot where the text caption goes in. And although it's not exactly the same type of text or doing exactly the same type of thing, the model gradually learns to understand instructions. And so I want to highlight that despite the fact that this training procedure only uses synthetic images and synthetic text instructions, we find that our method is able to generalize to both real images and human written instructions. So here's a real image. This is Leighton's Lady in a Garden. And the text instruction is make at a grocery store, which we wrote. And you can see that the output image has, shopping carts and shelves filled with vegetables and fruits. So it's pretty cool. And here's some more examples of real images. So it's kind of interesting the types of semantic edits that are performed. You can see that when it adds boats to the water, it makes the water a bit more turbulent. And when it adds skyscrapers in the distance in the top right, it also adds the corresponding reflections in the water. And by the way, speaking of editing real images, the text message animation I was showing before was actually using real editing results from our method. And this interface that is being shown here, the interface itself was a mock-up that was carefully animated by the first author of the paper, Tim. But since he made this, there have been tons of online apps that have wrapped our model in their interface to do almost exactly what we had imagined. So I should mention that a big part of why our results look good, as with most other diffusion models, is because of classifier-free guidance. And so basically, classifier-free guidance works by extrapolating the sampled latent or the noise in the direction of the conditional sample. And it's shown that this drastically increases sample quality. And so for our purposes, we add another dimension of classifier-free guidance, since we're operating on two conditional signals, both the image and the text instruction. And we have a particular formulation for this, which I won't get into details on, but you can see here that varying these two weights independently results in different types of edits. So increasing the image classifier free guidance, which is moving down the y-axis here, results in more adherence to the image content. It produces images that look more like the input image. And increasing the text classifier free guidance, moving across the x-axis here, results in more strong edits that respect the text instruction. And to find the ideal trade-off of these values and to evaluate our model, we used a couple of different clip-based metrics that measure the strength of the edit, or how well it agrees with the text, as well as the coherence with the input image. And so the two axes in this chart are sort of a trade-off where maximizing one leads to decreasing the other one. But you sort of want to get to the top right corner here. And we found through a bunch of experimentation that the amount of data and the variety of data, as well as the quality of the data, played a really big role in the model's ability to perform a diverse collection of edits. And you can see by the orange and the red curves here, which are operating on quite a bit less data, they aren't able to perform as significant image edits. And here's some baseline comparisons to some existing work in image editing, showing that basically our method was able to make more coherent and targeted edits to real images, preserving detail when appropriate and making changes only when needed. Oh, also, interesting discovery that we made along the way, there's a lot of bias in these models. So if you take the same image and you ask it to turn people into flight attendants or doctors or something like that, this tends to be heavily correlated with things like gender. And this is just one example of many ways that these models are biased. And the source is probably somewhere in the training data for Stable Diffusion or GPT-3. We're not really sure, but open to discussion on that. Anyways, a cool thing about our method is that we can produce different variations of the same requested edit by just varying the seed for the input noise. And so you can get, for one input example here on the left, which is this little cartoon character, you ask for it in a race car video game, you can get 4 different results. And in fact, you can keep getting more results by varying the seed randomly until you get something that you're happy with. And also, since our model is feed forward and is based on the latent diffusion model's architecture, it can operate at pretty high resolution. So here's an example of the creation of Adam at pretty high res. This is higher than the model was trained on. And we can change the image to put them in outer space. And it looks pretty good. Or we can take the people and we can turn them into robots. And lastly, one important thing about our model is that it takes just under 10 seconds to evaluate. And optimized versions of this can even run in under 5 seconds. So it makes it really easy to try out consecutive edits as if you were editing something inside of Photoshop. And the fact that it's so fast makes it really easy for us to use it in the loop for optimization, which is what we did in this project with Ayan, Matt, Alyosha, and Angju. So this project is called Instruct Nerf to Nerf. And the premise of this project was basically to enable the same type of editing that we were doing with Instruct Pix2Pix, but in 3D with, editing real captured nerf scenes. So here we've captured our friend Frederick, and we're turning him into a bronze statue, into Einstein, or into a clown, and so on. And so these are all 3D consistent edits that are coming out of the system based off of instructions. So under the hood, this method is really just Instruct Pix2Pix being used to gradually replace images in the NERF training dataset. So you start with a fully reconstructed NERF scene, and you gradually replace the images, which are the ones that are supervising the 3D scene, with edited versions of those same images using Instruct Pix2Pix. And so the editing here is happening iteratively in the loop, which is really only possible because our model is fast enough. And if you're familiar with Dream Fusion, this is a very similar setup. You could describe this sort of like as Dream Fusion, but starting with an existing scene and using a text and image conditioned diffusion model. And there are a few other nuances which I won't get into here, but we can talk about it offline afterwards. So the method can edit large scale real world scenes and can make a bunch of cool global edits, like changing the time of day, changing the weather, changing the environment. But it can also make more local contextual edits, which global 3D stylization approaches can't. So this is kind of important. And this is really thanks to the fact that we're using an instruction-based model. So we can refer to specifically the bear and replace it with a different type of bear without having to describe the whole scene. Or we can change a person's clothes and turn them into a marble or bronze statue, or make them a firefighter or whatever else. So pretty cool stuff. And here are some more results showing a comparison to some prior work in 3D stylization. And one of my favorite things about this is being able to turn objects in a NERF or a full NERF into basically a 3D painting, like in this Fauvism example in the top, or in the 3D Van Gogh in the top right. Like things that can't even exist. You can't even capture these things. And just like with Instruct Pix2Pix, there's also this classifier-free guidance term. So you can adjust this to get different magnitudes of changes in the scene. Oh, and this is a cool visualization that I want to show, which is showing the difference of what would happen if you were to just run Instruct Pix2Pix on every frame of a rendered 3D scene. So it's totally inconsistent on the right here. And the process of Instruct NERF to NERF will sort of take this noisy, inconsistent signal and distill it into a consistent 3D reconstruction that respects that edit. Okay, so to wrap up this part, I want to point out a couple of limitations of this method. So first of all, sometimes the edits from Instruct Pix2Pix are so 3D inconsistent that it's hard to consolidate them into a single consistent texture, like in this checkered example above. And sometimes Instruct Pix2Pix itself fails to make the edit, like in this example below where we're trying to delete the bear statue. And this actually brings me back to the topic of failure modes of Instruct Pix2Pix. So there are a bunch of types of edits that are hard for this model to do, but I'd say probably the biggest one is its inability to make structural edits, like the changing of spatial boundaries of objects, like zooming in, changing the size, moving things around, and so on. And this is largely because of a couple of things. First, it's the way that we condition the diffusion model by passing in a spatially aligned image concatenated along the channel dimension. And also, we don't have examples of spatial edits in the training data set, mainly because prompt to prompt operates by injecting attention maps, so it can't really perform meaningful spatial changes. And so we actually ended up exploring, the source of this problem of spatial manipulation in another project called Diffusion Self-Guidance. And this project was with Dave Epstein, Alan Jabri, Ben Poole, and Alyosha. And here's a picture of Dave. So in this project, we really focused on those last 10% of manipulative edits. Basically, how do we expose knobs on these image generation models that allow us to move objects around, change their size, replace them with other objects that we have in other images, or copy or alter their appearance? Like right now, you can generate an image like this one on the left using a text prompt, but what if I want to remove an object or make something bigger or duplicate it or move something around? It's nearly impossible to do this through text with some of these available diffusion models, but it really shouldn't be. Those modified images are almost certainly within the collection of images that these models can create. We just need to find a way to access them. So to spoil the reveal here a bit, here's what you can do with self-guidance. So given either a real or a generated image, here we're showing an example of a generated image with a croissant and a macaron splashing in the water in front of the Eiffel Tower. You can move objects around, without changing the rest of the scene. You can change the size of individual objects without changing the rest of the scene. You can replace objects in the image with any object from any other image, even an object from a real image. You can also inherit the appearance from another instance of the same object. You can also copy over the entire appearance from a different scene as sort of a per object or full image style transfer. Or you can borrow the composition or the layout from a different source image. And by the way, all of this is done without training a new model and without any extra data. It's just the guidance process during sampling time of a diffusion model. And just as a quick refresher, the diffusion sampling process is an iterative one where an image of random noise, ZT, is gradually denoised into a clean image by repeatedly querying a network, here we're calling epsilon theta, to get an estimate of the noise that's currently in the image, which here we're denoting as epsilon hat. These estimates are passed into an update function, which will remove some portion of the noise in the current noisy image, and this process is repeated until the image is noise-free. And a key capability of diffusion models is the ability to adapt outputs after training by guiding the sampling process. So from the score-based perspective, we can think of guidance as composing score functions to sample from richer distributions or to introduce conditioning on additional information. So in practice, using guidance involves altering the update direction epsilon hat t at each iteration. And we can do this with a classifier for our target distribution, or we can do this classifier free, which is something that's done in almost all text-image diffusion models these days. And so what we'd ideally want is to be able to find a guidance direction, like a classifier, that offers us the signal that we need for controlling these aspects that we care about, like object position, shape, size, and appearance. So how do we get that? Well, a lot of recent work has shown that the internals of these diffusion models contain a lot of useful information about the images that they're generating. So for instance, the attention operations that are performed inside the denoising units effectively bind objects to the image canvas. You know, they associate one object, as mentioned in the text prompt, with one part of the scene. So effectively, object localization should be able to be extracted from these attention maps. Similarly, it's been shown that the intermediate features of diffusion models capture the appearance and some semantic information about the objects in the scene. And this is actually the topic of a recent paper that we just put out, where we show that you can get really high quality correspondence, better than some of the state-of-the-art models, between pairs of images using the features inside a diffusion model. And here, correspondence can be extracted across real and generated images, and even across objects. So effectively, correspondences that will match semantically similar pixels, like a face on a dog will match with a face on a person, for example. And the way this works is by taking all of the feature maps that are used to generate an image, across all layers of the UNet and across all time steps of diffusion, and distilling them down into a single feature descriptor per pixel that can be used for matching. And it turns out there's a ton of really valuable information in those feature maps, so it works shockingly well. But anyways, back to the main story. So we know that attention maps and features contain a lot of the information that we might want to control with these added knobs that we want to add to this diffusion model. Features are encoding something useful about how things look, and attention is encoding where things go in the image. But what do we do with this information? Well, if we can design functions that extract this information from model intermediates, we can guide that information towards certain desired values. So in particular, we can define a set of properties we'd like to control, like for example, the centroid, the size, the shape, and the appearance of objects. And we can define ways of extracting these properties. Like for example, the centroid can be the weighted sum of pixel coordinates using the attention map as the weight, and the appearance can be the average feature value for pixels that belong to an object, and so on and so forth. So these are all properties extracted from the model itself at each step of the sampling process, and they can be guided to any target value that you choose. So just like before, where you could guide with a classifier, now you can guide with a target centroid, a target size, a target shape, or target appearance of any object in a generated image. And the neat thing about this is that with only these 4 properties, we can achieve surprisingly complex edits just by composing guidance with different combinations of these properties. So let me go through a collection of some of the types of edits that are possible with this. So here we're showing that you can modify the position and the size of objects. So for example, on the bottom here, we have a photo of a raccoon in a barrel going down a waterfall, and you can move this raccoon in a barrel up, down, left, right, however you choose, to any target location. And we can do the same with a couple other scenes, like this cat in a museum, or here we have the Tokyo Tower with the sun in the sky, and you can move around the sun. That's pretty cool. And in addition, you can also change the size of these objects. So make the sun bigger, make the sun smaller, all without changing the rest of the scene. And what I want to highlight here is the fact that for the most part, when making these modifications, most of the rest of the scene is staying the same, since the guidance procedure is actually guiding one object to change, but it's also guiding everything else to remain constant. And so we can also sample new appearances. If we guide everything to remain the same, but not apply any constraints on the appearance, we can effectively keep a given composition or a layout that we like, but sample new random appearances. So here we have a photo of a bear wearing a suit, eating a birthday cake out of the fridge, and we can decide that we like the composition on the first shot on the left, and we want to sample a bunch of different appearances, and that's what we have in the next few rows. And so this, by the way, is pretty similar to what prompt-to-prompt or ControlNet can do, and you can see what their results look like here. And since we can do things like guide both the structure and the appearance, this lets us do things similar to what we've seen in past GAN papers, where we can mix and match the appearance of the scene and the layout from different images. So here's our version of that, where along the diagonal, you see the original generated images, and along the x-axis, we're borrowing the appearance of that image. But not just the entire image appearance, but rather each object is borrowing the appearance, the appropriate appearance of the corresponding object in the other image. And along the y-axis, we're borrowing the layout from that image. So we can effectively mix and match appearance and layout. And another cool thing is we can just borrow the appearance from the image and sample a random layout, just as we were sampling random appearances before. So these last two columns are borrowing the appearance from the same row, but they select a random layout for the image. Okay, so far I've only been showing examples where we're editing generated images, but it's actually possible to use this for both, editing real images and also for borrowing appearance, layout, or objects from real images into generated images. So this might seem hard to do since we're relying on the intermediate representations in the diffusion model, and naturally, a real image isn't generated by the diffusion model, so it doesn't have those intermediates. But what we can do is approximate what those intermediates might have been by noising an image to every different time step and then running it through the diffusion model to get those intermediates. So this is sort of like a cheaper approximation of what we might get with inversion. And it turns out to work pretty well. So once we do this, we can use the appearance of an object from a real image, like this dog here, and we can borrow it when generating new images with different text prompts. Like here, we can put the dog into different outfits, like a chef or a purple wizard. Or we can take this teapot and stick it in the sea or make it pour out some tea. And if you're familiar with this literature, this might seem pretty similar to Dream Booth, and it is. Effectively, what we're doing here is sort of like a zero-shot version of Dream Booth. It doesn't require any model fine-tuning or any training to learn this particular object. It's just a sampling time procedure that guides the object to look like the one that we want. And it works with just one image, which is pretty impressive. So in the same way we can copy over the appearance of objects in a real image, we can also try to guide for reconstruction, effectively guiding the sampling process to match all of the properties that we've defined. So here you can see in the first row, this is a first column, this is a real image. And in the second column, this is our reconstruction by just guiding all of the properties in the generated image to match that of the real image. And then we can edit these properties to move things around or restyle them or resize them, and those are the rest of the columns. Okay, a couple final cool examples. So just as we can edit objects in the image, we can actually perform these edits on anything that's described in the text prompts. So this includes things like verbs or adjectives. So here's an example of an image that we generated with the prompt, a cat and a monkey laughing on a road. And we can see that the monkey is laughing, but not the cat. So we can actually move the word laughing, move its centroid to the right, and we get an image where the cat is laughing instead. And we can do the same thing with adjectives. So like here, without any other constraints, we have a messy room where the left half of the image looks messy. And if we move the messy token to the right, we get an image where the messy stuff is on the right side of the image. And this can be pretty useful for helping with attribute binding. So pretty often when generating images from text, we end up in this situation where we've described a bunch of objects, like here, a green hat, a blue book, yellow shoes, and a red jacket, but the model has a hard time binding all these attributes to their respective objects. So you can see that, the shoes are red instead of yellow and the jacket is yellow instead of red. But if we know that the word yellow corresponds to shoes and the word red corresponds to jacket, we can guide the position and the shape of those terms to match each other, which can fix this binding issue. So here we have the right thing. We have yellow shoes and we have a red jacket. Okay, one last example I really like. And so over the generation process, you can borrow individual objects and their appearances. So here we're showing that you've generated a bunch of different images with the same prompts, like this one in the top is a picnic blanket, a fruit tree, a car, and a lake. And you can pick and choose different object appearances from different images and mix them into a single image. And you get a plausible result with all the corresponding objects. So you see, we've borrowed the fruit tree with the red stuff on it, and we get that one on the right side. We've borrowed the white car from the third example, and we've borrowed the blue blanket from the first one. And you can even take it one step further, and you can guide the layout to match a particular target image. So here, we're taking all that stuff we were borrowing before, and we're also trying to get it to match the layout of this second to last column. Okay, so for this project, Dave created a set of hand-designed features, like centroid, size, shape, and so on. And these were designed to capture the properties from these model internals that I was talking about. But it's possible that these aren't the ideal choice. Like maybe an object's appearance lives in a certain layer and not in another, or maybe the shape lives in one attention map and not in another. And we can see these imperfections in our formulations sometimes through leakage. Like here, we have an example where we're only guiding the appearance of this line to match the top left image when generating a new image, but it actually ends up guiding the appearance and structure for the rest of the scene. And a similar thing can be seen here, where the position of two objects are entangled in the attention map, so their positions can't be separated. So when we move one object, both of them move. So anyways, this is more or less my concluding slide, and hopefully by now I've convinced you that a bit, at least, that we helped close the gap on some of these missing pieces of the artistic process. And maybe you've also seen some cool visuals along the way. And I'm sure by now, after about 40 minutes, you're sick of hearing me talk, but let me just conclude with a couple final thoughts on what my learnings or what my takeaways from these projects were. And these might be obvious for some of you, and these papers certainly aren't the first to explore them, but I think it might be a nice way of summarizing everything. So with Instruct Pixabix, I think my biggest takeaway was that, if you're going to train a model for anything involving image synthesis, if the output of whatever you're producing is an image, you should probably be fine-tuning an existing text image model instead. It'll be easier to train. You can use less training data, and you'll probably get better generalization. And also, if your task allows for it, you might consider training on generated synthetic data. Even if the data isn't perfect, as long as there's some signal, you can always use inference time sampling tricks to get images that look better than any one of your training examples. And another learning was that, instructions are a really great way of interacting with editing, as opposed to describing a full scene. Like if we wanted to edit the scene, normally we'd have to describe everything in there, like the bear, the background, what it's standing on, and so forth. But if we have instructions, we don't have to describe anything else. We can just say, turn the bear into a panda. Okay, so for these last two, I think the takeaway is that these generative models have a ton of useful information lurking just under the hood. And I think we've only just scratched the surface of making them useful, whether it be for controlling the images that they're spitting out, or for using those intermediate features or intermediate information for downstream tasks. Anyways, that's all the slides I have. So let me just thank all my co-authors for all their fantastic work on these projects, and thank all of you for listening.
Thank you, Alex. So, any questions from the audience?
Yeah.
Today is that there are limited modeling interactions within humans, or when, for example, you had this image where you were switching the colors of shoes and jacket, right? But it also changed the stack. So it's not the same jacket and shoe anymore, right? So what or do you think that it just retrieves such examples from what it has been trained on, or is it actually a generative process? Because from my personal experience with generative models, what I see is that maybe GANs and the AEs are better at preserving the semantics of your original data that you want to manipulate compared to diffusion models and such. And my second question is, can you also discuss a bit about the diversity when you sample these images? Because generally in the literature of diffusion models, we don't see the sample diversity being discussed as such. Whereas generative models inherently should have this feature of giving you diverse samples, and then you can choose which according to your personal experience. So what are your thoughts on that?
Yeah, so I think it's a trade-off, really. Like especially, so I glossed over this, but with using classifier-free guidance, you're effectively trading diversity for sample quality. And so this is something, it's a spectrum that you can move along. If you want more diverse results, you can apply less, but then you have fewer guarantees on the quality of your samples. So with respect to the example with the shoes and the jacket, I think it's true. I think it's possible that with tuning these guidance values some more, say if you wanted to tune it such that the appearance and shape of the objects that are in the second image match those in the first image, as we did in some of the previous examples, I'm sure you could do it. I think in this case, really, it was just the point was to make, if you're using a text-to-image model naively, you would get something on the left. But if you apply the constraints, like saying that the adjectives should match their appropriate nouns, you'd get something on the right. But I don't think any other guidance was applied here. So I think you could get the same thing you want on the left. This is just to show that you can force it to do the right binding.
Okay. Other questions, please?
You talked about appearance, features, layout information. I was curious if we can control the generative process by forcing it to preserve some pixels explicitly instead of implicitly. I'm not sure if that's been.
Sorry, one more time.
I was curious if we can control the spatial, the pixels that you change, and instead of changing the entire image, maybe you make really localized changes when you're trying to separate spatial information from appearance.
Yeah, that's an interesting idea. I mean, I think that the knobs that we've explored here are sort of high-level knobs, right? Like the centroid is aggregating a lot of the attention information. The shape is aggregating a lot of the attention information. But you could probably design similar knobs, although they'll be less useful in a lot of cases for moving things around. You probably could design similar knobs that say, this pixel should be identical to whatever other pixel. And there's a lot of this stuff has been explored in the space, like reconstruction guidance is one example, right? Like in the video diffusion models paper, that shows that if you know the pixel value, you can basically guide on that and force the result to respect it.
Please.
One question, you rely on a lot of underlying models that are kind of being updated over time, new versions come out. Have you noticed these techniques are robust to swapping output from the foundational model, or do they act completely?
Yeah, so that's a great question. This is something that we explored in a couple of these papers. In short, both for the diffusion hyperfeatures paper and for the self-guidance paper, we've hand designed a set of functions basically that take the internal representations of the model and turn them into something that's interpretable. And so that happens to work for a particular model, but if you take, say, you move from Stable Diffusion 1.4 to 2.1, it might not be, the layers that we're extracting for appearance may not be the optimal layers for appearance. And so the neat thing actually about diffusion hyperfeatures, which maybe let me find that slide, because I think the cool thing about this is that there's an aggregation network here that's trained for a particular task. So the paper on the whole was aiming at sort of extracting useful features from the diffusion, useful descriptors from the diffusion model features. But we were targeting the task of correspondence, and we said, okay, well, if we have some correspondence data, we can train this aggregation network to take all of those layers and all of those time steps and turn it into something that's useful for correspondence. And you can train that. You can do that same training process with different models, and you might get different weights in the way that they combine the individual feature layers. And we did actually show in the paper that, for Stable Diffusion 1.4 and 1.5 and 2.1, these are different layers. Like different layers in the model will actually have the most useful information for semantic correspondence or, pixel level details and so on. So yeah, it's changing. Even like, the same model trained on a few more examples will have, different statistics on where the useful stuff is.
Okay, other questions from the audience? Okay, so I think, thank you, Alex, for.
Cool.
Okay, so this concludes. We have a poster session actually, which will be started now from, what's the time from starting now essentially to 6 p.m. Our poster slots are number 64 to 83 and should be in the basement here in this building. So I take the occasion to thank you all for attending the workshop, and I hope we'll see you in next CVPR in 1 year from now. Thank you very much.